Consider the vast landscape of prime numbers, those indivisible integers that form the fundamental building blocks of all whole numbers, scattered seemingly at random throughout the infinite expanse of mathematics like stars across an unknowable sky. In the year 1859, a German mathematician named Bernhard Riemann proposed a deceptively elegant conjecture that would come to haunt the mathematical community for more than a century and a half, remaining one of the most profound unsolved mysteries in the discipline. The hypothesis concerns the distribution of these prime numbers and their relationship to what is known as the Riemann zeta function, a complex mathematical construct that produces a pattern of zeros that Riemann believed would always fall along a single straight line in an abstract multidimensional space called the complex plane. What makes this conjecture so profoundly troubling is not merely its difficulty, but rather the psychological weight of its implications. If Riemann was correct, then the seemingly chaotic arrangement of prime numbers throughout the integers follows a hidden harmony, an underlying order that permeates the mathematical universe itself. Generations of the world's finest mathematical minds have dedicated their careers to proving or disproving this single statement, employing increasingly sophisticated computational methods and theoretical frameworks. Yet the hypothesis remains stubbornly resistant to resolution despite its apparent simplicity when stated in plain language. The Riemann hypothesis has become normalized within the mathematical establishment as perhaps the most famous unsolved problem, with the Clay Mathematics Institute offering $1 million prize to anyone who can provide a proof. And yet this substantial incentive has failed to crack what remains an enigma shrouded in layers of analytical complexity that seems to transcend conventional problem-solving approaches. Consider the Collatz Conjecture, a deceptively simple mathematical statement that has haunted the minds of mathematicians for nearly a century, remaining unproven despite its elementary formulation and the seemingly infinite attempts by brilliant minds to resolve it. The conjecture begins with any positive integer you choose, and from there you apply a remarkably straightforward rule. If the number is even, divide it by 2, and if the number is odd, multiply it by 3 and add 1, then repeat this process indefinitely with your new result. The conjecture asserts that no matter which positive integer you begin with, no matter how large or seemingly random, you will eventually reach the number 1, at which point the sequence cycles endlessly through 1, 4, 2, back to 1 again. The psychological grip this problem maintains lies in its absolute accessibility combined with its absolute resistance to solution, for it requires no advanced mathematics to understand, yet has defeated the systematic approaches of professional mathematicians across generations. When you trace through the sequence manually for small numbers like 5 or 17, the numbers seem to dance chaotically upward and downward before mysteriously converging toward that singular destination of 1, as though pulled by some invisible mathematical gravity that we simply cannot articulate or prove exists. The mechanism that makes this so psychologically tormenting is that the conjecture exists in a peculiar space between the provably true and the mysteriously unresolved, where computers have verified it holds for trillions of numbers, yet remain unable to demonstrate why it must hold for all numbers, leaving us with empirical certainty divorced from logical proof. Imagine standing in a vast library where every even number greater than 2 has been written on an infinite shelf, and your task is to prove that each of these numbers can be expressed as the sum of exactly 2 prime numbers, a deceptively simple statement that has haunted mathematicians for nearly 3 centuries despite remaining fundamentally unproven. Goldbach's conjecture, first proposed by the Prussian mathematician Christian Goldbach in 1742, in a letter to the Swiss mathematician Leonhard Euler, presents one of the most elegantly straightforward, yet stubbornly resistant problems in mathematics, a puzzle that reveals how the simplest questions can possess the deepest mysteries. The conjecture merely suggests that every even integer greater than 2 can be written as the sum of 2 primes, and while this statement appears almost trivially obvious when you examine small numbers, 4 equals 2 plus 2, 6 equals 3 plus 3, 8 equals 3 plus 5, 10 equals 5 plus 5. The proof that this pattern continues infinitely has proven to be an intellectual wall that refuses to yield to conventional mathematical approaches. The psychological mechanism underlying our fascination with Goldbach's conjecture stems from the profound tension between simplicity and complexity. where a child can understand the statement within moments. Yet the world's greatest mathematical minds have been unable to construct a definitive proof, despite centuries of effort and the advent of computational technology that has verified the conjecture for numbers exceeding 4 quintillion. We have normalized the persistence of this unresolved problem by treating it as a fundamental feature of mathematical reality itself, accepting that some truths may be so deeply woven into the fabric of number theory that they resist proof through any method currently available to human intelligence, suggesting perhaps that certain mathematical realities exist beyond the reach of formal demonstration. Imagine standing in an infinite library where every book is labeled with a number, and you are tasked with finding pairs of books whose numbers differ by exactly 2. You might find books numbered 3 and 5, then 5 and 7, then 11 and 13, 17 and 19, and 29 and 31. These are the twin primes, pairs of prime numbers separated by the smallest possible gap, and as you walk deeper into this library, the books become increasingly sparse and harder to locate. The Twin Prime Conjecture proposes that no matter how far you venture into this infinite collection, you will never reach a point where these paired books simply stop appearing entirely. It asserts that there exist infinitely many twin prime pairs, yet mathematicians have never been able to prove this seemingly straightforward statement despite centuries of investigation. The psychological mechanism underlying our obsession with this problem stems from a fundamental human need for pattern completion and categorical certainty. When we observe a pattern repeating across numerous instances, 3 and 5, 11 and 13, 29 and 31, our minds naturally extrapolate this pattern into infinity, assuming that what has held true so far will continue holding true forever. We construct an intuitive narrative where the pattern should persist, because we have witnessed no definitive reason for it to terminate. Yet the conjecture remains unproven, because the distribution of prime numbers resists simple formulas and predictable behavior, defying our attempts to establish a logical framework that would guarantee their infinite pairing. We have normalized the existence of this unsolved problem by accepting it as one of mathematics' greatest mysteries, even though its resolution would require either an elegant proof confirming our intuitions or a surprising counterexample demolishing them. This normalization allows us to rest comfortably with uncertainty, treating the conjecture as a permanent fixture in the mathematical landscape rather than an anomaly demanding resolution. Imagine you are sitting in a vast library containing millions of books, and someone hands you a completed jigsaw puzzle and asks you to verify that it is correct by examining whether all the pieces fit together properly, which takes you only a few minutes to confirm through careful inspection. Now imagine that same person asks you to create that same puzzle from scratch, starting with a blank table and thousands of loose pieces, with no image to guide you, which would require hours or even days of trial and error and systematic arrangement. This fundamental asymmetry between verification and creation lies at the heart of one of computer science's most profound and troubling questions. Whether the class of problems whose solutions can be quickly verified, known as NP, is actually equivalent to the class of problems whose solutions can be quickly found, known as P in the real world of computation. Thousands of problems exhibit this peculiar characteristic where checking a proposed answer is dramatically faster than discovering that answer in the first place, from breaking encryption codes to scheduling airline flights to discovering new medicines. The psychological mechanism underlying our acceptance of this disparity stems from our intuitive understanding that creation requires exploration, while verification requires only comparison. Yet no mathematician has ever proven whether this intuition reflects a fundamental truth about the universe or merely a limitation of our current algorithmic approaches. We have normalized this inequality despite its lack of logical justification because our entire modern digital infrastructure depends upon it, particularly cryptography systems that protect financial transactions and classified information, which would catastrophically fail if P somehow equaled NP and problems we assume are hard to solve suddenly became easy. Imagine standing before an infinite library where the books are organized not by subject or author, but by the very nature of infinity itself, and you're tasked with determining whether there exists a collection of books whose size falls somewhere between the countably infinite shelves of whole numbers and the uncountably infinite expanse of all real numbers on a number line. A question that has haunted mathematics since Georg Cantor first formalized the concept of different sizes of infinity in the late 1800s. The Continuum Hypothesis proposes that there is no such intermediate infinity, that the infinity of real numbers is the immediate successor to the infinity of natural numbers with nothing in between, yet despite more than a century of rigorous mathematical investigation, this statement remains neither provably true nor provably false within our standard mathematical framework. The psychological mechanism underlying our struggle with this problem stems from our deep intuitive discomfort with infinity itself, for our minds evolved to process finite quantities in finite spaces, and when we attempt to reason about the infinite, we find ourselves grasping at concepts that slip through the fingers of logic like water, unable to construct a meaningful comparison between infinities because our internal mental models simply lack the necessary architecture. Picture a river flowing steadily around a bend, or imagine stirring honey into your morning coffee and watching the swirls dissolve into the liquid with graceful, predictable patterns. These everyday observations of fluid motion seem to follow rules we can almost touch, as if the universe has written down the equations that govern how water moves through pipes, how air currents form around an airplane wing, or how blood circulates through our veins. Yet when mathematicians attempted to capture these observations in precise mathematical language during the 18th and 19th centuries, they created a system of equations called the Navier-Stokes equations, which describe how fluids behave under the influence of pressure, viscosity, and external forces. For nearly 200 years, these equations have proven extraordinarily useful in engineering and physics, accurately predicting fluid behavior across countless real-world applications. However, a fundamental question remains utterly unresolved. Under certain initial conditions, do these equations always produce smooth, well-behaved solutions that flow infinitely into the future without developing singularities or sudden discontinuities? The question sounds abstract, almost ethereal, yet it sits at the heart of understanding whether the mathematical description we have created truly captures something fundamental about how nature operates. This is the Navier-Stokes smoothness problem, one of the 7 Millennium Prize problems, each worth $1 million to whoever can prove or disprove the conjecture. The paradox lies in the disconnect between our intuitive experience and mathematical certainty. We observe smooth fluid motion everywhere around us, yet we cannot rigorously prove that the equations describing these motions maintain their smoothness in all theoretical scenarios. Mathematicians have begun to suspect that solutions might occasionally develop infinite velocities or pressures at isolated points, creating what physicists call turbulence, yet proving this possibility or its impossibility remains perpetually beyond reach. Imagine a universe where the most fundamental forces that bind reality together operate according to equations so elegant and symmetrical that they seem to predict particles with no mass whatsoever. Yet in every laboratory experiment we conduct, we observe these particles behaving as if they possess measurable weight and resistance. This is the essence of the Yang-Mills mass gap problem, one of the 7 Millennium Prize problems that remain unsolved after decades of intense mathematical scrutiny. The Yang-Mills theory itself emerged from the work of physicists Chen-Ning Yang and Robert Mills in the 1950s, describing how certain force-carrying particles, known as gauge bosons, interact with matter through elegant mathematical symmetries. The theory has proven remarkably successful in describing 3 of the 4 fundamental forces in nature, yet it contains within it a deeply troubling inconsistency that no amount of calculation has been able to resolve. The mathematical framework predicts that gluons, the particles responsible for the strong nuclear force that holds quarks together inside protons and neutrons, should theoretically be massless, similar to photons. However, the universe does not cooperate with this prediction. Instead, we observe that these gluons cannot propagate freely as isolated particles. They become confined within matter through a phenomenon called color confinement, and the energy required to isolate them creates what appears to be an effective mass. This gap between what the equations promise and what nature delivers represents perhaps one of the most profound mysteries in theoretical physics. The problem has persisted despite tremendous effort from the world's greatest mathematical minds, resisting both computational approaches and abstract theoretical innovations. We have grown somewhat accustomed to this paradox, integrating it into our working models of particle physics as if it were merely another technical detail to be managed rather than a fundamental crack in our understanding of reality itself. Imagine standing in a vast library where each book represents an equation, and within those equations live invisible creatures called elliptic curves, mathematical objects defined by deceptively simple polynomial expressions that have captivated mathematicians for centuries with their profound and elusive properties. The Birch-Swinnerton-Dyer conjecture, proposed in 1965 by Brian Birch and Peter Swinnerton-Dyer, makes a remarkable claim about the relationship between two seemingly unrelated mathematical quantities: the number of rational solutions that exist on an elliptic curve, and a special function called the L function that encodes deep arithmetic information about that same curve. The conjecture asserts that whenever the L function equals 0 at a particular critical point, the elliptic curve should possess infinitely many rational solutions, and conversely, when the L function does not vanish at that point, only finitely many solutions should exist. What makes this conjecture so psychologically unsettling is that these two mathematical objects appear to operate in completely different universes of discourse, one belonging to the ancient geometric tradition of studying curves and their integer points, while the other emerges from complex analysis and the mysterious properties of infinite series and analytical continuation. Despite decades of computational verification and partial theoretical progress, mathematicians remain unable to prove this profound connection, unable to bridge the conceptual gap between the visible arithmetic structure of elliptic curves and the invisible analytic shadows cast by their L functions. Deep within the abstract corridors of algebraic geometry, there exists a proposition so elegant in its formulation, yet so resistant to proof, that mathematicians have spent over 70 years contemplating its truth without resolution. A situation that presents itself as a peculiar kind of intellectual frustration, where the closer one examines the problem, the further understanding seems to retreat. The Hodge Conjecture, formulated by William Valence Douglas Hodge in the 1941st year, proposes that certain mathematical objects called Hodge classes on non-singular projective algebraic varieties can always be written as rational linear combinations of classes derived from algebraic cycles, which is to say that the deepest topological structures of these geometric spaces should be reducible to simpler algebraic components, suggesting a profound unity between geometry and algebra that we cannot quite grasp. The mechanism underlying this conjecture operates through a layered mathematical construction where one begins with algebraic varieties, which are geometric shapes defined by polynomial equations, and then applies sophisticated tools from homology and cohomology theory to understand their structure, revealing patterns and symmetries that appear to follow from algebraic properties but whose necessity remains mysterious and unproven. This conjecture has become one of the 7 Millennium Prize problems, offered by the Clay Mathematics Institute with a monetary reward of $1 million for its resolution. Yet despite this incentive, and despite the efforts of the world's finest mathematical minds across generations, the problem refuses to yield to conventional approaches, suggesting that either the conjecture is true but requires entirely new mathematical frameworks to prove, or it is false in ways that current theory cannot detect. Consider the simple equation where 3 positive integers, labeled a, b, and c, are related by the constraint that a plus b equals c, and where these numbers share no common factors beyond 1, a property mathematicians call being coprime. The ABC conjecture, proposed in 1985 by mathematicians Joseph Easterl and David Masser, makes a deceptively elegant claim about the relationship between these numbers and their prime factorizations, suggesting that whenever such a relationship exists, the product of all distinct prime factors dividing a, b, and c cannot be significantly larger than c itself, with only finitely many exceptions to this rule. What makes this conjecture so intellectually unsettling is that it appears almost self-evidently true when you examine specific examples, yet proving it rigorously has eluded the mathematical community for nearly 4 decades, creating a peculiar cognitive dissonance between intuition and formal demonstration. The conjecture gained renewed prominence when Japanese mathematician Shinichi Machizuki claimed in 2012 to have developed a proof using radical new mathematical machinery called interuniversal Teichmuller theory, a framework so abstract and unfamiliar that the mathematical establishment has struggled to verify his work, leading to an extended period of cautious skepticism that persists today. The deeper psychological mechanism at work here involves our tendency to trust patterns that feel obvious, until we attempt the Herculean task of formal verification, revealing the vast gulf between recognizing something intuitively and constructing an ironclad logical argument a gap that has become normalized in modern mathematics, where many conjectures rest in this uncomfortable liminal space between apparent truth and unattainable proof. The ABC conjecture has also become emblematic of a broader challenge in contemporary mathematics: the tension between individual genius and collaborative verification, between the pursuit of increasingly abstract frameworks and the fundamental human need for shared understanding and consensus within the mathematical community. Consider the peculiar category of numbers known as perfect numbers, which possess the remarkable property that the sum of their proper divisors equals the number itself, a quality so elegant and rare that mathematicians have sought them for millennia with an almost obsessive dedication. The first perfect number is 6, whose divisors 1, 2, and 3 sum precisely to 6 itself, a mathematical harmony that feels almost too neat to be real. The second is 28, followed by 496 and 8128, each one sitting in isolation like precious gems scattered across the number line at increasingly vast distances from one another. Now here exists a question that has haunted mathematics for over 2,000 years, ever since the ancient Greeks first pondered this mystery, and it concerns whether there might exist even a single odd perfect number, a perfect number that cannot be divided evenly by 2. The strange psychological pull of this problem stems from the fact that every perfect number we have ever discovered is even, every single one without exception, and yet no one has ever proven that an odd perfect number cannot exist. This creates a peculiar cognitive dissonance, a gap between what we observe and what we can definitively prove, which keeps mathematicians returning to this problem across generations like waves perpetually lapping against the same shore. What makes this particularly maddening is that we have proven so many other profound truths about perfect numbers, such as the fact that every even perfect number follows a specific pattern discovered by Euclid over 2,000 years ago, and yet this question persists in its stubborn opacity, refusing to yield to proof or disproof despite the combined intellectual efforts of countless brilliant minds. We have developed increasingly sophisticated arguments suggesting that odd perfect numbers, if they exist, must be astronomically large and possess an improbably specific structure, yet each argument stops just short of achieving the absolute certainty that would constitute a proof. Consider a rectangular box, a three-dimensional form built from 6 rectangular faces, where every edge possesses a measurable length and every angle holds the precision of perfect right angles. Now imagine that this cuboid, this ordinary geometric solid, contains within itself a peculiar property. Every single measurement of this object, without exception, is a whole number. The length is a whole number, the width is a whole number, the height is a whole number. But then imagine pushing further into the mathematical depths of this shape, demanding that the 3-faced diagonals, those lines running across the surfaces from one corner to another, must also each be whole numbers. And finally, the ultimate demand, the space diagonal, that magnificent line cutting through the interior of the cuboid from one corner to the diametrically opposite corner, must likewise resolve to a whole number. A shape where every conceivable measurement, from the most obvious dimensions to the hidden internal distances, expresses itself perfectly in integers. Mathematicians have searched for such an object for centuries, applying computational power, developing sophisticated algorithms, and employing theoretical frameworks, yet no one has ever found an example of this perfect cuboid, and simultaneously, no one has proven that such an object cannot exist. The human mind recoils at this liminal space between confirmed impossibility and theoretical possibility, at a mathematical object that may or may not inhabit the realm of reality, suspended indefinitely in a state of profound uncertainty. We continue to search because the alternative, accepting that we simply do not know, feels somehow incomplete, leaving us in contemplation of whether perfection in all dimensions remains eternally elusive or merely waits patiently to be discovered. Imagine yourself in a practical situation that countless people encounter during the ordinary events of daily life. You have purchased a large, comfortable sofa that you deeply desire to place in your living room, but there exists a significant obstacle between you and your goal, specifically a narrow corridor with a sharp right-angle turn that your sofa must navigate in order to reach its intended destination. You stand before this geometric puzzle with your furniture handlers, all of you wondering whether the sofa will actually fit through the turn, and if so, what angle must be achieved, what maneuvers must be executed, and what precise dimensions would allow the largest possible sofa to make this journey successfully. This simple, everyday practical problem transforms into one of mathematics' most elegant and stubbornly unsolved puzzles, one that has captivated professional mathematicians and casual thinkers for decades without yielding a definitive answer. The moving sofa problem asks us to determine the largest area of a two-dimensional shape that can navigate through an L-shaped corridor of unit width, meaning a hallway 1 unit wide that turns at a right angle into another hallway also 1 unit wide, with the shape able to rotate and maneuver in any way necessary. The psychological mechanism underlying this problem's persistent appeal lies in how it transforms an immediately relatable human experience into an abstract mathematical inquiry that demands precision, yet remains tantalizingly beyond our grasp. We understand the real-world scenario viscerally, we can visualize the physical constraints, yet the mathematical solution remains elusive despite centuries of mathematical development. Researchers have established boundaries around the answer, proving that the maximum sofa area must be somewhere between approximately 2.2 and 2.8 square units. Yet no one has determined the exact value or confirmed the precise shape that achieves this maximum, despite sophisticated computer analysis and countless theoretical approaches from accomplished mathematicians worldwide. Imagine you are holding a simple closed curve, perhaps a smooth loop drawn on a piece of paper, and you are asked a deceptively straightforward question. Does there exist a square whose 4 corners all touch this curve simultaneously? This is the inscribed square problem, a question that has haunted mathematicians for over a century, resisting proof despite its apparent simplicity and intuitive appeal. The problem emerged formally in the early 1900s, though its origins trace back to earlier geometric investigations, and it asks whether every simple closed curve in the plane must contain an inscribed square, that is, 4 vertices of a square that lie exactly on the curve itself. For many common shapes like circles and ellipses, the answer is obviously yes, and we can visualize these squares with ease, their corners resting perfectly upon the smooth boundaries. Yet when we venture into more complex territory, when curves become increasingly irregular or peculiar in their construction, the certainty evaporates entirely. The psychological mechanism at work here involves our deep-seated intuition that geometric constraints should yield to mathematical inevitability, that a curve cannot somehow dodge every possible square configuration, that symmetry and structure must emerge from apparent chaos. We assume that because the problem seems so elementary, so fundamental to our understanding of plane geometry, a proof must surely exist, tucked away in some advanced theorem or elegant construction that we simply have not yet discovered. The persistence of this problem, despite countless attempts by brilliant minds, reveals something profound about the gap between intuitive mathematical expectation and rigorous logical demonstration, and it has become normalized in mathematical discourse as one of those tantalizing open questions that reminds us how little we truly understand about the basic properties of curves, even after centuries of geometric study and exploration. Imagine a single sphere suspended in the void of 3-dimensional space, perfectly round and complete unto itself, and now imagine surrounding it entirely with other identical spheres, each one touching the central sphere at exactly one point, like planets orbiting a star made of glass. The question that mathematicians have pondered for centuries is deceptively simple. How many of these identical spheres can simultaneously kiss that central sphere without any 2 of them touching each other? This is the kissing number problem, and it exists at the intersection of geometry, topology, and the fundamental architecture of spatial relationships. In 2 dimensions, the answer is 6 spheres, or circles rather, arranged around a central circle like petals on a flower, and this fact was known to ancient geometers. In 3 dimensions, the problem becomes vastly more complex and elusive, a puzzle that resisted definitive solution until the late 20th century. The kissing number in 3-dimensional space was proven to be exactly 12 spheres, though the proof required computational verification and mathematical rigor so intense that it took decades for the mathematical community to fully accept it. Yet even with this resolution, the problem persists in higher dimensions, where the answer becomes increasingly mysterious and counterintuitive, with some dimensions remaining completely unknown to us despite our advanced understanding of geometry. What makes this problem so philosophically troubling is that it reveals how spatial relationships operate according to principles that defy our intuitive expectations, and how even something as fundamental as the arrangement of touching objects in space contains depths of mystery that only rigorous mathematics can begin to penetrate. Imagine a circular track where multiple runners begin at the same starting point and run at different constant speeds, each one maintaining their own unique pace without variation or rest. As time progresses, these runners will spread out around the track, moving at their distinct velocities, sometimes clustering together and sometimes drifting far apart from one another. The lonely runner conjecture proposes that for each runner on this track, there will eventually come a moment in time when that particular runner finds themselves completely alone, separated from all the other runners by a significant distance, existing in isolation while others occupy different sections of the circular path. This fundamental question asks whether every runner, regardless of how the speeds are chosen, will eventually experience their own period of solitude where they stand apart from the entire group. The psychological intrigue of this conjecture emerges from its paradoxical nature. It seems intuitively obvious that runners moving at different speeds must eventually space themselves far enough apart that at least one runner achieves separation. Yet mathematically proving this elegant statement has resisted decades of rigorous analysis from some of the world's most capable mathematicians. The mechanism underlying the conjecture involves the intricate interplay between periodic motion, rational and irrational numbers, and the distribution of points around a circle in ways that defy simple calculation. When speeds have rational relationships to one another, patterns emerge with regularity, but when irrational numbers enter the equation, the complexity multiplies exponentially, creating scenarios where the mathematical structure becomes nearly impossible to penetrate with conventional proof techniques. What makes the lonely runner conjecture particularly fascinating is how it demonstrates the boundary between mathematical intuition and rigorous proof, existing as a statement that feels undeniably true yet remains stubbornly unproven except in limited cases, suggesting that perhaps our logical frameworks contain gaps we have not yet learned to see. Imagine you are sitting in a theater watching a film that has captivated you for 2 hours with compelling characters, intricate plotting, and genuine emotional investment. And then in the final 15 minutes, the narrative suddenly pivots toward resolution in a way that feels mathematically inevitable yet somehow unsatisfying, as though the screenwriter made calculations based on audience expectations rather than the logical trajectory of the story itself. This is the happy ending problem, a phenomenon where our collective desire for positive conclusions becomes so powerful that it distorts the mathematical probabilities and narrative logic that should otherwise govern outcomes. The mechanism operates through a curious inversion of rational thought, wherein we collectively agree to accept narrative conclusions that contradict the causal chains we have witnessed throughout the preceding story, creating what might be called an emotional override of logical consequence. When we examine stories with statistical rigor, we find that happy endings occur at rates far exceeding what the established rules and circumstances would predict, suggesting that somewhere in the creative process, an invisible hand adjusts probability in favor of human satisfaction. The psychological driver behind this phenomenon relates to our deep neurological need for closure and meaning, combined with our desire to believe that effort and goodness are rewarded rather than randomly distributed across an indifferent universe. We have normalized this so thoroughly that we now experience genuine cognitive dissonance when stories end according to their established logic rather than conforming to our emotional requirements. This creates a peculiar situation where storytellers face genuine pressure to violate the mathematical integrity of their narratives, knowing that audiences will reward emotional satisfaction over philosophical consistency, and we have collectively constructed entire industries around this willing suspension of causality. Picture yourself sitting alone in a mathematician's study, surrounded by countless papers filled with equations and numerical patterns, contemplating one of the most deceptively simple yet profoundly mysterious statements in modern number theory, a conjecture so elegant in its formulation that it seems almost impossible that no one has been able to prove or disprove it despite decades of intense academic scrutiny and computational verification. The Beal Conjecture, named after the banker and mathematics enthusiast Andrew Beal, who formulated it in 1993, makes a strikingly straightforward claim about the relationship between exponents and prime numbers that, while intuitive in its presentation, conceals depths of mathematical complexity that have resisted every attempt at resolution. The conjecture states that if we take the equation a to the power of x plus b to the power of y equals c to the power of z, where a, b, c, x, y, and z are all positive integers, and where x, y, and z are all greater than 2, then A, B, and C must share a common prime factor, which means they cannot be relatively prime to one another in the way that would create a counterexample. What makes this conjecture so psychologically compelling is how it seems to whisper something fundamental about the hidden architecture of numbers, suggesting that the universe of mathematics operates according to principles so deep and interconnected that, when exponents grow large enough, the numbers involved must inevitably reveal their kinship through shared prime divisors. The psychological mechanism at work here involves our human tendency to perceive patterns and symmetries in mathematical structures, and to assume that such patterns must reflect underlying truths about reality itself, creating an intuitive sense that the conjecture simply must be true because it feels right, because it aligns with our aesthetic sense of how numbers should behave when subjected to the pressure of exponential growth. Consider the deceptively simple fraction of 4 divided by any number greater than 1, and imagine trying to express this single quantity as the sum of exactly 3 unit fractions, where each unit fraction has a numerator of 1 and a denominator that is some positive integer. This is the essential puzzle at the heart of the Strauss conjecture, a problem so elementary in its statement that a child could understand it, yet so persistently resistant to proof that some of the greatest mathematical minds of the 20th and 21st centuries have devoted considerable effort to solving it without complete success. The conjecture asserts that for every integer n greater than 1, the equation 4 divided by n can always be written as the sum of exactly 3 unit fractions with distinct denominators, a claim that has been verified computationally for extraordinarily large values yet remains unproven in its universal form. What makes this conjecture particularly fascinating is the contrast between its apparent simplicity and its remarkable depth. For while mathematicians have discovered countless patterns and special cases where the conjecture holds true, they have simultaneously failed to establish a general proof that would settle the matter once and for all. The psychological allure of this problem lies in its accessibility combined with its elusiveness, attracting both professional mathematicians and amateur enthusiasts who believe their particular approach might finally crack the barrier that has stood for decades. Over time, researchers have become somewhat inured to the difficulty, accepting that some problems resist the most obvious attack strategies and instead require entirely novel mathematical frameworks or insights that may not yet exist, creating a peculiar state of mathematical limbo where the conjecture is likely true but remains fundamentally unresolved. Consider the deceptively simple question that has haunted mathematicians for nearly 2 centuries. Are there any solutions to the equation where n factorial plus 1 equals m squared other than the 3 known cases of n equals 4, n equals 5, and n equals 7? This is Brocard's problem, named after the French mathematician Henri Brocard, who first posed it in 1876. And it represents one of those rare mathematical mysteries that appears trivial on its surface yet has resisted all attempts at resolution with remarkable stubbornness. When we examine the 3 known solutions, we find that 4 factorial plus 1 equals 25, which is 5 squared, 5 factorial plus 1 equals 121, which is 11 squared, and 7 factorial plus 1 equals 5041, which is 71 squared. The peculiar spacing of these solutions, with increasingly large gaps between consecutive n values, suggests that perhaps no other solutions exist at all. Yet proving this conclusively remains fundamentally elusive despite the considerable computational power applied to searching for additional cases far beyond what Brocard himself could have imagined. The psychological mechanism underlying this problem's persistence lies in the profound difficulty of proving negative results in mathematics. For disproving the existence of something across an infinite domain requires a form of logical machinery that often simply does not exist in our current mathematical arsenal. We have grown accustomed to leaving such questions suspended in uncertainty, neither proven true nor proven false, existing in a liminal space where our intuition suggests one answer, yet our inability to construct a proof forces us to acknowledge the limitations of human mathematical reasoning, and accept that some patterns may remain fundamentally unknowable despite their apparent simplicity. Consider the landscape of prime numbers as they scatter across the infinite expanse of positive integers, and imagine the peculiar gaps that emerge between consecutive primes like unfilled spaces in an otherwise crowded theater. In 1808, the French mathematician Adrien-Marie Legendre observed something deceptively simple yet profoundly mysterious. Between any two consecutive perfect squares, such as the space between 4 and 9, or between 9 and 16, there always seems to exist at least one prime number. This observation, now known as Legendre's conjecture, states that for every positive integer n, there exists at least one prime number between n squared and the quantity n plus 1 squared. The conjecture is elegant in its simplicity, yet it remains unproven after more than 2 centuries of mathematical investigation. What makes this conjecture so psychologically compelling is that it describes a pattern that our minds can intuitively grasp, a rhythm to the distribution of primes that suggests some underlying order or principle governing their placement across the numerical landscape. When mathematicians verify this pattern computationally for billions upon billions of integers, the consistency of the observation reinforces a deep intuition that such a principle must exist, that there must be some logical reason why the gaps between consecutive primes never grow too large in this particular way. Yet despite this overwhelming empirical evidence and the combined efforts of countless mathematical minds employing increasingly sophisticated techniques, no one has managed to construct a rigorous proof that would elevate this conjecture to the status of a proven theorem. We have become remarkably comfortable with this state of uncertainty, accepting that some patterns persist in mathematics without requiring immediate logical justification, as if the universe itself operates by rules that occasionally elude our current frameworks of understanding. Imagine a grid of numbers arranged in a perfect square, where each row, each column, and each diagonal all sum to the identical value, a property known as a magic square. Now imagine attempting to construct such a grid using only perfect squares, numbers like 1, 4, 9, 16, 25, and so on, integers multiplied by themselves. This seemingly elegant mathematical puzzle has haunted researchers for centuries because despite our intuitive sense that such an arrangement should exist, no one has ever successfully created a magic square composed entirely of perfect squares, nor has anyone conclusively proven that one cannot exist. The pursuit of this object has become a meditation on mathematical impossibility, a problem that persists in the liminal space between proven falsehood and undiscovered truth. The psychological mechanism that keeps mathematicians engaged with this puzzle operates through a peculiar form of cognitive tension, where the simplicity of the question, "Can you arrange perfect squares in this specific pattern?" belies the complexity of the answer, creating a false sense that a solution must lurk somewhere just beyond the reach of current mathematical tools and techniques. We have become accustomed to living with this uncertainty, accepting that some problems simply refuse resolution despite decades of computer searches and theoretical investigation. And perhaps this acceptance itself normalizes the idea that mathematical reality need not conform to our sense of aesthetic order or logical expectation, that the universe of numbers operates according to rules indifferent to human intuition and desire. Yet this very resistance has proven oddly productive. In chasing the magic square of squares, mathematicians have developed new techniques for understanding Diophantine equations, discovered unexpected constraints on how numbers can be arranged, and mapped the terrain of mathematical possibility itself, transforming a failed quest into a landscape of genuine knowledge, even if the original object remains forever elusive. Imagine a collection of mathematical sets, each containing various elements, arranged in such a way that whenever you take any two sets from this collection and combine them into their union, the result is guaranteed to also belong to the original collection itself. This is what mathematicians call a union-closed family of sets, a concept that seems remarkably restrictive at first glance. Yet the question of what such families must contain has haunted the discipline since 1979, when Peter Frankl first posed it as a conjecture. The conjecture states something deceptively simple. In any finite union-closed family of sets that contains at least one non-empty set, there must exist some element that appears in at most half of all the sets in the family. This statement sounds almost obvious when you first encounter it, a modest claim that should follow naturally from the constraints of the union-closed property, and yet no mathematician has managed to prove it rigorously, nor has anyone constructed a counterexample that definitively disproves it. The psychological mechanism underlying this unsolved problem reveals how our mathematical intuition can mislead us into believing something should be true without providing the rigorous machinery to demonstrate it. We construct mental models of union-closed families and observe that certain elements appear in fewer sets while others appear more frequently, yet the claim that some element must appear in at most half the sets remains elusive. Mathematicians have verified this conjecture holds true for small cases and special families, building confidence that it represents a genuine truth rather than a false lead. Yet this very confidence may be exactly what has allowed the problem to persist for decades. Imagine yourself sitting in a room with a collection of colored markers, and someone asks you a deceptively simple question. What is the minimum number of colors needed to color every point in an infinite two-dimensional plane such that no 2 points at exactly 1 unit distance apart share the same color? This is the essence of the Hadwiger-Nelson problem, a question that has haunted mathematicians since 1950, quietly residing in the background of chromatic graph theory without yielding its answer. The problem sounds almost whimsical, like a children's puzzle about painting an infinite landscape, yet it carries profound implications for our understanding of how geometry, distance, and color theory intersect in abstract mathematical space. The psychological mechanism that makes this problem so persistently frustrating is that we possess boundaries but not a solution. Mathematicians have proven that you need at least 4 colors, and they have also shown that 5 colors always suffice. Yet the true answer nestled somewhere between these numbers remains elusive, tantalizing us with the possibility that the answer could be 4, 5, or theoretically something we have not yet imagined. What makes the Hadwiger-Nelson problem particularly maddening is that despite decades of computational effort and the application of sophisticated mathematical techniques from combinatorics, geometry, and graph theory, we have somehow normalized this ignorance, treating the gap between 4 and 5 as an acceptable ambiguity in a field that typically demands precision. The problem persists not because it is unsolvable or because mathematicians lack sufficient brilliance, but because the infinite nature of the plane creates an environment where our traditional proof strategies seem inadequate, and we have come to accept that some questions about infinity may resist the logical frameworks we have built to contain them. Imagine a gathering of people at a large conference, and your task is to determine the minimum number of attendees required to guarantee that either 5 of them form a complete group of mutual friends, or 5 of them form a complete group of mutual strangers, with no exceptions and no possibility of escape from this certainty. This is the essence of Ramsey theory, a branch of mathematics that concerns itself with finding order within apparent chaos, and the specific value known as R55 represents one of the most tantalizing unsolved puzzles in this field. What makes R55 so maddening is that mathematicians have determined its boundaries with remarkable precision, yet the exact number remains stubbornly elusive, like a word on the tip of your tongue that refuses to fully materialize. We know with absolute certainty that R55 is somewhere between 43 and 48, a range that seems impossibly narrow, and yet that final answer has resisted the combined efforts of the world's greatest minds for decades. The psychological torment of this problem lies in its fundamental simplicity wrapped in computational impossibility. The question itself is easy enough for a child to understand, yet solving it requires either a mathematical insight of extraordinary brilliance or computational resources so vast that even our most powerful computers would need centuries to verify a definitive answer through exhaustive search. The reason this particular Ramsey number has proven so resilient is that the number of possible colorings and configurations grows explosively as the variables increase, transforming what should be a straightforward counting problem into a combinatorial nightmare of staggering proportions. We have normalized this failure, this gap in human knowledge, by treating R55 as simply one more unsolved problem in a long list of mathematical mysteries, yet it represents something profound about the limits of human understanding. A problem so elementary in its statement that explaining it requires mere minutes, yet so infinite in its complexity that solving it may require centuries or prove to be fundamentally beyond our reach. Imagine a needle, infinitesimally thin and of fixed length, placed on an infinite flat plane, and consider the profound question that has haunted mathematicians for over a century. What is the smallest possible area of a region in which you can rotate this needle through a complete 360-degree revolution, returning it to its original position and orientation? This deceptively simple geometric puzzle, posed by Japanese mathematician Soichi Kakeya in 1917, conceals within it layers of mathematical complexity that have resisted resolution despite the concentrated efforts of some of the greatest minds in modern mathematics. The intuition that guides most people suggests that a circular region would suffice, or perhaps a shape only marginally more efficient, yet the Kakeya conjecture proposes something far more unsettling: that the minimum area should be zero, that you could theoretically rotate a needle of any length whatsoever within an arbitrarily small region through any angle you desire. The psychological mechanism underlying this conjecture operates through a peculiar mathematical insight, one that emerges when you abandon the rigid constraints of rigid body rotation and instead allow the needle to move and deform its path in increasingly exotic ways, creating shapes with infinitely crinkled boundaries and fractal dimensions that seem to collapse the area toward nullity while maintaining the ability to complete the necessary rotation. What makes this conjecture particularly vexing is that mathematicians have proven related results that seem to corroborate its truth in lower dimensions, while simultaneously discovering that extending these principles to higher dimensional spaces creates contradiction and paradox, suggesting that either our understanding of dimensional geometry is fundamentally incomplete, or that the conjecture itself may harbor a subtle logical flaw that remains perpetually obscured. Buried beneath layers of mathematical abstraction that continue to perplex even the most dedicated researchers. Consider the humble Rubik's Cube, that iconic puzzle of twisted layers and colored squares that has captivated minds since its invention in the 1970s, and within its mechanical simplicity lies a question that has haunted mathematicians for decades. How many times can any given position on the cube be reached through different sequences of moves? David Singmaster, a mathematician fascinated by the cube's mathematical properties, observed something peculiar when analyzing the vast landscape of possible cube configurations and the various paths one might take to reach them. He noticed that certain positions appeared to be reachable through an unusually large number of distinct move sequences, far more often than random probability would suggest they should be, as though the cube's structure possessed some hidden bias toward particular configurations. Singmaster's conjecture proposes that there exists a fixed upper bound to how many different ways any position on a Rubik's Cube can be reached, regardless of which position you examine, meaning that even the most accessible configuration cannot be approached through an unlimited number of distinct paths. The psychological mechanism at work here involves our deep-seated expectation that complexity should distribute evenly, that all endpoints in a sufficiently large mathematical space should be equally reachable and equally obscure. Yet the Rubik's Cube defies this intuition with its layered structure and rotational symmetries, creating unexpected clustering patterns. Despite decades of computational power being applied to this problem, the conjecture remains unproven, existing in that peculiar liminal space where mathematicians have verified it for millions upon millions of cube positions through brute force calculation, yet cannot articulate why it must be universally true through logical derivation alone. Imagine you have a sequence of prime numbers laid out before you, stretching infinitely from 2, 3, 5, 7, 11, and so on through all the known primes that mathematicians have discovered and verified across centuries of computational effort. Now imagine taking the differences between each consecutive pair of these primes, subtracting each prime from the one that follows it, creating a new sequence that emerges from the gaps between them. What Norman Gilbreth noticed in 1958, while performing these calculations by hand during what should have been an ordinary evening, was that if you apply this same differencing operation repeatedly to subsequent sequences, always working with the absolute differences, and always starting fresh with the primes arranged in their natural order, something remarkable appears to happen. The first element of every sequence generated by this process of successive differencing, no matter how many times you repeat it, seems to always equal 1. This observation, elegant in its simplicity yet profound in its implications, became known as Gilbreth's conjecture, a statement so apparently consistent across all tested cases that it has stubbornly refused verification through logical proof for over 6 decades. Mathematicians have computed this pattern for the first millions and billions of primes, running sophisticated algorithms across increasingly powerful computers, and in every single instance the pattern holds true without exception. Yet despite this overwhelming empirical evidence, despite the conjecture's elegant formulation and its apparent universality, no one has succeeded in demonstrating why this must be true through the rigorous machinery of mathematical logic. The mechanism underlying this observation remains shrouded in mystery, as if the primes themselves are protecting a secret about their own structure and distribution that defies our current frameworks of understanding. In the vast landscape of prime numbers, those peculiar integers divisible only by one in themselves, mathematicians have long observed patterns that seem almost too regular to be coincidental, patterns that suggest an underlying order to the apparent chaos of their distribution. Craméer's conjecture, proposed by the Swedish mathematician Harold Craméer in 1936, makes a specific and strikingly bold claim about the gaps between consecutive prime numbers, suggesting that the space between any prime number and the next prime number should never be significantly larger than the square of the logarithm of that prime itself. This conjecture emerges from careful observation of how prime numbers scatter themselves across the number line, clustering densely at first, and then becoming progressively sparser as numbers grow larger, and yet somehow maintaining a kind of predictable sparsity that refuses to deviate wildly from mathematical expectation. The psychological mechanism underlying why mathematicians find this conjecture so compelling rests partly on our deep human inclination to perceive order and structure even in seemingly random phenomena, to believe that the universe operates under rules of elegant consistency rather than arbitrary chaos, and to assume that the foundation of all arithmetic must be governed by some underlying rational principle. What makes Craméer's conjecture particularly fascinating is that despite countless computational verifications confirming its accuracy across billions upon billions of prime numbers, no mathematician has ever managed to prove it rigorously from first principles, nor has anyone found a counterexample to definitively disprove it. This peculiar state of affairs has persisted for nearly 90 years, with the conjecture remaining simultaneously so plausible and yet so frustratingly out of reach that it has become normalized within mathematics as one of those elegant mysteries that defines the frontier of human knowledge. A reminder that even in our most rigorous fields, absolute certainty often eludes us no matter how compelling the evidence. Consider the peculiar landscape of prime numbers, those indivisible integers that have fascinated mathematicians for millennia, standing as the fundamental building blocks of all natural numbers, and among the many unsolved mysteries concerning their distribution and properties, exists a conjecture proposed by Doron Andrica in 1985 that appears deceptively simple yet remains frustratingly unproven despite decades of computational verification and theoretical investigation. The conjecture itself states that the gap between consecutive prime numbers, when subjected to a specific mathematical operation involving square roots, should always remain smaller than 1, a statement so elegantly understated that it seems almost trivial. Yet this very simplicity masks a profound complexity that has resisted the combined efforts of mathematicians worldwide. When we examine the gaps between successive primes like 2 and 3, 5 and 7, or 11 and 13, the differences appear manageable and unremarkable. But as numbers grow larger and primes become increasingly sparse, the question of whether these gaps ever violate Andrica's proposed boundary becomes genuinely uncertain, forcing mathematicians to confront the possibility that their intuitions about number theory might harbor subtle flaws. The psychological mechanism underlying our relationship with this conjecture stems from the human tendency to perceive patterns in sequences, and to assume that observed regularities in small cases will naturally persist in larger ones, creating a false sense of security that the conjecture must be true simply because no counterexample has emerged after testing millions upon millions of prime pairs. Imagine standing before an infinite sequence of numbers, each one a prime separated from the next by an even gap, and consider that Alphonse de Polignac proposed in 1852 that for every even number, no matter how large, there exists an infinite number of prime pairs that are separated by precisely that distance. This conjecture suggests that if you choose any even number, say 2, then you will find infinitely many twin primes like 11 and 13, or 17 and 19, gaps of exactly 2 throughout the endless landscape of numbers. Similarly, if you select an even number like 6, the conjecture claims there are infinitely many prime pairs separated by 6, such as 5 and 11 or 11 and 17, and this pattern should repeat infinitely for every conceivable even gap. The psychological mechanism underlying our fascination with this conjecture emerges from humanity's deep need to find patterns and order within the seemingly chaotic distribution of prime numbers, those fundamental building blocks of arithmetic that refuse to follow any simple formula. We observe these prime gaps empirically, discovering pair after pair across billions of numbers, and our minds naturally extrapolate this evidence into a universal principle, assuming that what we see repeated so frequently in the accessible range must continue eternally in the unreachable distances beyond our computational reach. Yet despite centuries of effort by mathematicians, despite computers checking trillions upon trillions of numbers and finding no counterexamples, nobody has proven that Polignac's conjecture is actually true, nor has anyone definitively proven it false. We have normalized this uncertainty by continuing to search, by building increasingly sophisticated algorithms, by treating the conjecture as probably true while acknowledging we possess no logical foundation for certainty, accepting that some patterns visible to our perception may remain forever beyond our capacity to validate with absolute mathematical rigor. Consider the peculiar category of prime numbers named after the 18th century French mathematician Sophie Germain, who discovered a remarkable property while investigating Fermat's last theorem, a relationship so elegant that it seems almost designed by intention rather than emerging from the natural structure of integers themselves. A Sophie Germain prime is a prime number p such that 2 multiplied by p plus 1 is also prime, creating pairs of numbers with an almost musical symmetry where 5 becomes 11, 11 becomes 23, 23 becomes 47, each transformation preserving this mysterious primality across the doubling operation. The numbers that result from this transformation, called safe primes, exhibit their own peculiar beauty and significance, appearing frequently in cryptographic systems and security protocols that protect digital communication across the modern world. Yet their distribution through the infinite landscape of integers remains utterly mysterious and seemingly random despite our most sophisticated analytical approaches. Mathematicians have observed that Sophie Germain primes appear to become increasingly sparse as numbers grow larger, yet they seem never to disappear entirely, suggesting an underlying pattern that has eluded proof for generations, creating a nagging sense that we are missing something fundamental about the architecture of numbers themselves. The psychological mechanism at work here involves our deep human need to find order and predictability within mathematical systems, coupled with the profound disorientation that occurs when we discover that some patterns persist without any logical explanation we can articulate or prove. We have normalized this uncertainty by incorporating these unresolved questions into our modern cryptographic systems, essentially building the foundation of digital security upon mathematical properties we do not fully understand, transforming our ignorance into pragmatic utility, while the underlying mystery continues to haunt every encryption transaction occurring simultaneously across billions of devices. Imagine a mathematician sitting at their desk, staring at numbers that follow a peculiar pattern, numbers of the form 2 to the power of p minus 1, where p itself must be prime, and among these carefully constructed values, certain ones emerge as prime themselves, called Mersenne primes, named after the 17th century monk Marin Mersenne who first catalogued them. And this mathematician knows that we have discovered only 51 of these elusive numbers as of the early 21st century. With the largest containing over 24 million digits, yet here exists a question so fundamentally simple that it has tormented mathematicians for centuries. Are there infinitely many Mersenne primes, or do they eventually cease to exist altogether? The psychological mechanism underlying this particular conundrum stems from our deep human need to find patterns and order within the chaotic realm of numbers. And when we discover a sequence like Mersenne primes, our minds naturally extrapolate forward, assuming that if the pattern has appeared this many times already, surely it must continue indefinitely into the mathematical infinite. Yet this intuition has proven catastrophically unreliable throughout the history of mathematics. Where countless sequences we assumed infinite turned out to be finite, and conversely, many we assumed finite revealed themselves to be boundless. Consider the peculiar mathematical objects known as Fermat primes, those rare and elusive numbers that follow a deceptively simple formula, 2 raised to the power of 2 raised to the power of n plus 1. Pierre de Fermat discovered the first 5 of these numbers in the 17th century, and their apparent abundance seem to suggest an infinite procession of such primes extending indefinitely into the numerical abyss, a confident prediction that has haunted mathematics ever since. We know today that only 5 Fermat primes have ever been discovered or verified: 3, 5, 17, 257, and 65,537, and despite centuries of computational effort, intensive searching, and the application of modern algorithmic techniques that can process millions of calculations per second, no 6 Fermat prime has emerged from the numerical fog. This absence, this conspicuous silence where we expected continuation, creates a peculiar cognitive tension, because mathematicians cannot definitively prove whether the remaining Fermat primes simply do not exist, or whether they remain hidden beyond our current computational reach, waiting in some inaccessible region of the number line. The psychological mechanism underlying this conundrum involves our natural human tendency to extrapolate from observed patterns, to assume that a sequence that begins with clear regularity will continue according to similar rules. Yet mathematical reality frequently betrays such intuitions, presenting us instead with abrupt terminations and unexpected breakdowns in what seemed like logical progression. We have normalized this uncertainty by accepting that certain mathematical questions may remain perpetually open, neither provably true nor provably false within our current framework of knowledge, allowing us to continue our work while acknowledging that the Fermat primes may represent an exhausted category, a finite collection masquerading as an incomplete one, forever leaving us suspended between conclusion and continuation. Imagine a mathematical landscape so sparse and peculiar that mathematicians have spent over a century searching for objects that might not even exist in abundance. And this is precisely the realm of Wieferich Primes, a category of prime numbers so extraordinarily rare that only 2 have ever been discovered despite exhaustive computational efforts that have examined trillions upon trillions of candidates. A Wieferich prime is defined by a deceptively simple condition. It is a prime number p such that 2 raised to the power of p minus 1, when divided by p squared, leaves a remainder of 1, a property that seems almost impossibly restrictive and yet mathematically sensible in its formulation. The first such prime, 1793, was discovered in 1913, and the second, 3311, was found in 1935, and since that time, despite computational searches extending into the trillions, no third Wieferich prime has surfaced, suggesting either that they are incomprehensibly rare or perhaps that only finitely many exist. The psychological weight of this mathematical pursuit rests on a peculiar foundation. Mathematicians have constructed entire theoretical frameworks around objects whose fundamental existence remains uncertain, creating conjectures and theorems that hinge upon properties of numbers that may be functionally impossible to find in practice. This mirrors a strange human tendency to develop elaborate systems of thought around absent or vanishing entities, investing intellectual energy into the pursuit of ghosts that may never materialize. And yet this pursuit is not futile, because the very exploration of Wieferich primes has illuminated deep connections between number theory, cryptography, and computational methodology. What persists here is a remarkable tolerance for incompleteness, a willingness to accept that certain mathematical questions may remain eternally open, and that the search itself, regardless of outcome, generates knowledge and understanding that enriches the entire landscape of mathematical inquiry. Consider the elegant spiral of a nautilus shell, the arrangement of sunflower seeds, the branching of trees. These natural phenomena follow the Fibonacci sequence, a mathematical pattern so fundamental that it appears woven into the fabric of organic growth itself. Within this sequence, where each number is the sum of the 2 preceding numbers, there exists a peculiar subset that captures the imagination of mathematicians worldwide. The Fibonacci primes, those rare instances where a Fibonacci number is also a prime number divisible only by itself and 1. We know of several such numbers, 5, 13, 89, 533, yet the deeper we search, the more elusive they become, and this is where the mystery takes hold of us. The question that haunts researchers is deceptively simple. Are there infinitely many Fibonacci primes, or does the sequence eventually exhaust itself, leaving only composite numbers in its wake? The human mind gravitates toward patterns and completeness, toward the sense that if something begins in abundance, it should continue indefinitely, yet mathematics refuses to guarantee this comfort. We have searched through billions of Fibonacci numbers without discovering a definitive proof either way, and this absence of closure creates a peculiar psychological tension, a mathematical cliffhanger that has persisted for decades. The paradox deepens when we consider that the Fibonacci sequence itself is infinite and well-defined, its generation as automatic as counting, yet the primes within it remain fundamentally unpredictable, their distribution following no known formula or law. We have constructed computational models and conducted empirical searches, accumulating evidence that suggests Fibonacci primes might indeed be infinite, yet without rigorous proof, this remains merely conjecture, a hypothesis supported by observation rather than logical necessity. Consider the peculiar intersection of two mathematical properties that should, by all reasonable logic, have nothing to do with one another. A number that reads identically forwards and backwards, and a number divisible only by one in itself. When these properties align, we encounter palindromic primes, numbers like 11, 101, 313, 9999, and increasingly rare examples as numbers grow larger. The mathematical community has long observed that palindromic primes exist at all, and yet their distribution follows no discernible pattern that mathematicians have been able to reliably predict or explain. 5 is palindromic and prime, 7 is palindromic and prime, 11 is palindromic and prime. But then the next palindromic prime is 101, and after that comes 131, then 213, then 231, with the intervals between these twin properties becoming increasingly erratic and difficult to anticipate. What fundamentally troubles mathematicians is that there appears to be no mathematical reason why the property of being a palindrome should correlate with the property of being prime at all. And yet these numbers continue to appear, defying the expectation that they should be vanishingly rare or follow some elegant formula. The deeper mystery involves whether infinitely many palindromic primes exist, a question that remains unproven despite centuries of investigation, and this uncertainty haunts the field because we have proven that there are infinitely many primes, and we understand that palindromes occur naturally within the decimal system. Yet the marriage of these two concepts produces a sequence whose ultimate behavior remains fundamentally unknowable. In the early 20th century, the German mathematician Edmund Landau posed 4 deceptively simple conjectures about the fundamental nature of prime numbers, questions so elegantly stated that they seem as though they should have been solved decades ago, yet they remain completely unresolved more than a century later, standing as monuments to the hidden complexity lurking beneath mathematical simplicity. The first conjecture proposes that there are infinitely many primes that are 2 apart from another prime, known as twin primes, such as the pairs 11 and 13, or 29 and 31, pairs that seem to scatter throughout the number line in a pattern that mathematicians have intuited must continue forever, yet no one has ever managed to prove it. The second problem asks whether every even number greater than 2 can be expressed as the sum of 2 primes, a variation on the Goldbach conjecture that feels almost obvious when you test small numbers, discovering that 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, but this pattern becomes progressively harder to verify and prove as numbers grow larger. The third problem questions whether there are infinitely many primes of the form n squared plus 1, integers where you take a number, square it, add 1, and find yourself with a prime, a sequence that produces primes like 2, 5, 17, 37, and 101, creating an almost hypnotic rhythm of mathematical coincidence. The fourth problem seeks to determine whether there is always a prime between consecutive perfect squares, suggesting that between n squared and the quantity n plus 1 squared, there exists at least one prime number, a notion that feels intuitively correct and matches our experience with small numbers, yet resists formal proof despite centuries of mathematical progress. Consider the peculiar landscape of polynomial mathematics, where Polish mathematician Andrzej Szkindel proposed in 1958 a sweeping conjecture so general and so fundamental that it encompasses countless other unsolved problems as mere special cases. And this hypothesis suggests that for any finite collection of irreducible polynomials with integer coefficients and positive leading coefficients, there exist infinitely many positive integers n for which all the polynomials simultaneously produce prime numbers, provided only that no prime divides the product of all these polynomials for every possible integer input. The psychological mechanism at work here involves our deep human intuition that primes should distribute themselves with remarkable generosity throughout the output of polynomial equations, an intuition born from observing patterns in small numbers and extrapolating them to infinity with perhaps unwarranted confidence. What makes Skinzel's hypothesis H so profoundly disorienting is that it remains completely unproven despite being almost certainly true according to heuristic arguments and computational evidence. Yet its consequences are so far-reaching that mathematicians have built entire frameworks of conditional results upon it, essentially constructing elaborate theoretical cathedrals upon foundations that have never been secured. We have somehow normalized the practice of proving theorems that begin with phrases like assuming Skinzel's hypothesis H or contingent upon the truth of hypothesis H, creating a strange mathematical culture where we openly acknowledge uncertainty while simultaneously proceeding as though the conjecture were established fact. And this peculiar state of mathematical suspension persists decade after decade, generation after generation, with no clear path forward emerging from either computational experiments or theoretical innovation, leaving the field in a kind of perpetual limbo where progress depends upon resolving something we cannot quite reach. Imagine standing before an infinite corridor of numbers, each one a polynomial expression waiting to reveal its secrets, and you are tasked with determining which of these mathematical functions will ever produce a prime number at all. This is the essence of the Bunyakovsky Conjecture, named after the Russian mathematician Viktor Bunyakovsky, who first proposed this tantalizing claim in 1850, suggesting that if you take any irreducible polynomial with integer coefficients and a positive leading coefficient, and if this polynomial is not divisible by any prime for all integer inputs, then this polynomial must produce infinitely many prime numbers as you substitute larger and larger integers into it. On the surface, this seems like a reasonable extension of what we already know about simpler cases, yet mathematicians have spent nearly 2 centuries unable to prove it or decisively disprove it, making it one of the most stubbornly resistant problems in number theory. The psychological mechanism driving our difficulty here stems from the fact that polynomials behave with apparent simplicity that masks profound underlying complexity, and we naturally expect that if a polynomial can generate primes at all, it should generate them infinitely often. Yet this intuition crumbles when we attempt to construct a rigorous proof that accounts for all possible cases and exceptions. What makes this conjecture particularly fascinating is that we have verified it for countless specific polynomials, and the evidence overwhelmingly suggests it is true, yet the general proof remains elusive, existing in that frustrating mathematical space where empirical observation and logical certainty refuse to align, forcing mathematicians to accept that sometimes even the most plausible patterns require defensive walls of proof that may take generations to construct, or may never be constructed at all. Consider the elegant simplicity of Leonard Eugene Dixon's conjecture, proposed in 1913, which concerns itself with the behavior of polynomial sequences and their divisibility properties, a mathematical assertion so fundamental in its scope that it remains unproven more than a century later despite the efforts of countless mathematicians working across generations. Dixon's conjecture states that for any finite set of linear polynomials in one variable, where each polynomial has a positive leading coefficient and the polynomials share no common factor, there exist infinitely many positive integer values such that all polynomials in the set simultaneously yield prime numbers, with the singular exception that if such a set is specifically constructed to prevent this through divisibility constraints, then only finitely many such simultaneous prime occurrences exist. This conjecture extends and generalizes the Twin Prime Conjecture, the Cousin Prime Conjecture, and numerous other celebrated unresolved problems in number theory into a single unified framework that encompasses an almost bewildering breadth of mathematical territory. The psychological mechanism underlying why this conjecture persists so stubbornly is rooted in how mathematicians have normalized the incompleteness of their fundamental understanding regarding prime distributions, accepting as routine the phenomenon that certain logical truths appear arithmetically self-evident yet resist formal proof through all available mathematical techniques. We have developed an almost meditative acceptance of encountering theorems that seem obviously true, that behave true in every empirical test, and yet remain eternally inaccessible to proof, creating a peculiar intellectual space where conviction and uncertainty coexist without resolution. allowing us to continue advancing mathematical knowledge while consciously acknowledging that some foundational principles may lie beyond our grasp. Deep within the landscape of number theory lies a deceptively simple observation that has quietly resisted proof for decades, a conjecture so elegantly stated that its complexity seems almost deliberately hidden beneath layers of mathematical innocence. Grimm's conjecture, proposed by Carl Albert Grimm in 1969, concerns itself with the distribution of prime numbers and their relationship to composite numbers in an unexpectedly intimate way. The conjecture suggests that if you take any set of consecutive composite numbers, you can always assign to each composite number a distinct prime divisor that divides it, and remarkably, each composite number receives a different prime divisor than its neighbors receive. To illustrate this principle, consider a sequence of composite numbers between two consecutive primes. The conjecture maintains that you can assign prime factors to these composites in such a manner that no two adjacent composites share the same assigned prime divisor. What makes this proposition so intellectually captivating is that it appears intuitively reasonable, almost obvious when you first encounter it, yet mathematicians have found themselves perpetually unable to establish its truth or falsity with absolute certainty. The conjecture touches upon something fundamental about how prime numbers scatter themselves through the integers, how they govern the structure of composite numbers, and how the gaps between primes contain hidden patterns and relationships that seem to follow an almost deliberate organizational principle. Despite numerous computational verifications extending to extraordinarily large numbers, despite the conjecture holding true in every single case ever examined by both human mathematicians and computer algorithms, a general proof remains elusive, suspended in that peculiar mathematical limbo where evidence overwhelmingly suggests correctness but logical necessity refuses to materialize. Imagine a landscape of numbers stretching infinitely into the distance, each prime number standing like a solitary sentinel in an otherwise populated terrain, and consider the curious observation that these primes seem to maintain a peculiar spacing from one another, a regularity that appears almost too consistent to be mere coincidence. Firuzbach's conjecture, proposed by the Iranian mathematician Farideh Firuzbach in 1982, suggests that the gap between consecutive prime numbers follows a surprisingly strict pattern, specifically that the nth prime number, when taken as a fractional exponent of itself, decreases as you move further along the sequence of primes. In other words, if you take the ratio of each prime to the previous one, raise it to the power of 1 divided by n, this value should monotonically decrease, creating a descending sequence that never reverses course. This is a statement so elegant in its simplicity, yet so profound in its implications, because it describes an underlying architecture to the distribution of primes that we have observed empirically across billions upon billions of primes, yet cannot prove theoretically. The conjecture represents a deeply human attempt to impose order and pattern onto what appears to be chaos, to find the hidden melody within what seems like random noise, and despite the computational verification of this pattern holding true for the first trillion prime numbers, we remain unable to prove it must always continue to hold. The persistence of this unproven conjecture in the landscape of number theory reflects our tendency to trust patterns we observe repeatedly, to believe in regularities we have validated countless times, even when the logical apparatus required to demonstrate why such patterns must necessarily exist forever remains just beyond our grasp, suspended in the fog of mathematical possibility. Oppermann's conjecture presents itself as a deceptively simple statement about the distribution of prime numbers, yet it has eluded proof or disproof since Dane Ludwig Oppermann first proposed it in 1862, making it one of mathematics' most persistently enigmatic claims about the fundamental building blocks of arithmetic. The conjecture asserts that for every integer greater than 1, there exists at least one prime number between n squared and n squared plus 2n, and simultaneously, at least one prime number between n squared plus 2n and n plus 1 squared, essentially claiming that the gaps between consecutive primes never grow too large in a very specific and particular way. What makes this conjecture psychologically fascinating is how it operates at the intersection of apparent randomness and hidden order. For while prime numbers seem to scatter themselves throughout the integers in patterns that appear almost chaotic to the casual observer, Oppermann's statement suggests an underlying regularity so strict that it would guarantee primes cluster together in predictable intervals at certain scales. The mechanism driving our continued inability to resolve this conjecture likely stems from the fact that while we can verify it computationally for billions upon billions of cases, each individual verification tells us almost nothing about whether the pattern must hold universally, creating a frustrating gap between empirical evidence and logical certainty that haunts number theory. Despite having no logical reason why this particular arrangement of primes should behave exactly as Opperman described, mathematicians have largely normalized the existence of this unsolved problem, treating it almost as furniture in the landscape of open questions, never quite forgotten yet rarely commanding the urgent attention devoted to more famous conjectures like the Riemann Hypothesis or the Twin Prime Conjecture. Even though its resolution might illuminate equally profound truths about how primes distribute themselves through the infinite expanse of natural numbers. Imagine a vast plane where you have drawn a circle of a particular radius centered at the origin point, and your task is simply to count how many lattice points, those integer coordinate positions where both the horizontal and vertical values are whole numbers, fall within the boundary of that circle. This is the Gauss circle problem, named after Carl Friedrich Gauss, one of history's most prolific mathematicians, who encountered this deceptively simple question while investigating the distribution of these discrete points. The problem seems almost trivially straightforward when you consider it at first, for you need only examine each point with integer coordinates and determine whether its distance from the center remains less than or equal to the radius you have specified. Yet beneath this surface simplicity lies a mathematical gulf that has confounded some of humanity's greatest minds for more than 2 centuries. The actual count of lattice points approaches the area of the circle as the radius grows larger, which makes intuitive sense, but the error term, that mysterious remainder representing the difference between the actual count and what the area formula predicts, refuses to follow any pattern that mathematicians have been able to discern with certainty. This error term sometimes behaves smoothly, sometimes erratically, sometimes clustering in ways that suggest hidden structure, yet always managing to evade definitive capture. Mathematicians have proven various upper bounds for how large this error can possibly grow, yet no one has definitively established the precise rate at which it must grow under all circumstances. The problem persists despite being stated in language a schoolchild could understand, demonstrating how the most profound mathematical mysteries often hide themselves within questions that appear almost trivial, and how the boundary between what seems knowable and what remains fundamentally elusive continues to perplex us even when we possess vastly superior computational power than Gauss himself could have imagined. Consider the seemingly simple question of counting divisors. If you take any positive integer and ask how many whole numbers divide evenly into it, you receive a straightforward answer. Yet when mathematicians began asking what happens when you sum up all these divisor counts across many numbers simultaneously, they stumbled into a problem that has resisted complete understanding for nearly 2 centuries. The Dirichlet divisor problem emerges from this innocent inquiry, asking us to find the average number of divisors among all integers up to some large number n, and more specifically, to determine the exact error term when we try to approximate this sum with a formula. Peter Gustav Lejeune Dirichlet discovered that the average behaves roughly like logarithm of n, a beautiful result, yet the precise magnitude of the deviation from this estimate remains tantalizingly unknown. The psychological mechanism underlying our difficulty here involves the interaction between order and chaos in number theory. Divisors follow no predictable pattern, they cluster randomly throughout the integers, and when we aggregate their behavior across millions of numbers, our intuition fails us completely because we cannot visualize the cumulative effect of countless irregular distributions. What makes this problem particularly maddening is that we have narrowed the answer down considerably through centuries of computational effort and theoretical refinement, establishing upper and lower bounds that grow increasingly tight, yet we still cannot pinpoint the exact exponent that would describe how quickly the error term must grow. We have normalized this incompleteness by treating the Dirichlet divisor problem as a fundamental mystery of mathematics, accepting that some questions seem to require deeper axioms or entirely new frameworks to answer. And perhaps this acceptance itself demonstrates how thoroughly we have incorporated the limits of mathematical knowledge into our understanding of what it means to seek truth in abstract domains. Consider the elegant partnership between the numbers 220 and 2804, two ancient figures that share a remarkable bond that mathematicians have contemplated for over 2,000 years. When you sum all of the proper divisors of 220, those numbers less than itself that divide evenly into it, you arrive precisely at 2804, and remarkably, when you perform the identical operation upon 2804, you return exactly to 220, creating what is known as an amicable pair. These numbers embrace each other across the numerical landscape in perfect reciprocal harmony, each one containing within its divisors the complete sum of the other, a mathematical reflection of friendship itself encoded into the very structure of integers. Since the Pythagoreans first documented this phenomenon, mathematicians have discovered hundreds upon hundreds of such pairs, progressing from ancient examples like 1018 paired with 1098 through medieval discoveries, to modern computational reveals of pairs involving numbers with thousands upon thousands of digits. Yet despite centuries of intensive investigation, despite computers searching through billions upon billions of integers, humanity remains entirely uncertain whether the supply of these amicable pairs is finite or infinite, whether there exists some ultimate pair beyond which no others can be found, or whether they continue forever in an endless procession through the number line. The fundamental question persists unresolved and seemingly untouchable through conventional mathematical approaches, tantalizing researchers with its simplicity of statement paired against its impenetrable elusiveness, representing one more instance of mathematical reality where our certainty dissolves into profound mystery despite our advanced understanding of numerical structures. Imagine a number, any number, and begin a peculiar mathematical journey where you repeatedly find the sum of all its proper divisors, those factors that divide evenly into your starting number but exclude the number itself. Take the sum you've calculated, then repeat this process with that new number, creating an endless chain of numerical transformations that some mathematicians have spent decades tracing by hand and computer alike. This is the fundamental premise of Aliquot sequences, and what makes them genuinely unsettling is that we do not know with certainty whether these sequences always eventually arrive at a predictable destination, or whether some sequences will wander eternally through the integers without ever settling into a pattern. Starting with 5, for instance, the sequence flows downward. 5 yields 1, and 1 yields 0, creating a complete and satisfying closure. Yet when you begin with 95, the numbers climb and descend in a complex dance, eventually arriving at the perfect number 28, where the cycle becomes stable and locked. But when mathematicians launched similar sequences from other starting points like 186, something infinitely more troubling occurs. The numbers appear to climb without bound, potentially ascending forever into regions of astronomical magnitude, or they may eventually collapse back down through patterns we haven't yet identified. The psychological mechanism underlying our fascination with Aliquot sequences stems from humanity's deep need to find patterns, closure, and predictability within mathematical systems that appear deceptively simple on their surface, yet harbor complexity that eludes even our most powerful computational machines. Consider for a moment the peculiar category of numbers that mathematicians have designated as untouchable, a classification that exists in the realm of number theory as a silent and largely unexplored frontier. An untouchable number is defined as a positive integer that cannot be expressed as the sum of the proper divisors of any other number, where proper divisors are all the positive divisors of a number excluding the number itself. For instance, the number 2 is untouchable because no matter how extensively you search through the integers, you will never find another number whose proper divisors sum precisely to 2. The first few untouchable numbers are 2, 5, 52, 88, and 196, and despite centuries of mathematical inquiry, mathematicians have been unable to prove whether untouchable numbers exist infinitely or whether they eventually cease to appear among the integers. This absence of proof regarding their fundamental nature creates an intellectual liminal space where we operate with intuition rather than certainty, accepting these orphan numbers into our taxonomies without truly understanding their deeper significance. The psychological mechanism underlying our relationship with untouchable numbers involves a kind of mathematical resignation, where we encounter a phenomenon that appears to follow no particular pattern or rule, yet we continue to classify and catalog it anyway, deriving comfort from naming what we cannot explain. What makes this situation particularly vexing is that untouchable numbers seem to serve no practical purpose in applied mathematics or physics, existing purely as abstract curiosities within number theory, and yet they persist in mathematical consciousness as objects worthy of study and contemplation. We have normalized this pursuit of understanding the seemingly meaningless by embedding it within the larger context of pure mathematics, where the absence of practical application becomes a virtue rather than a liability, and where the investigation of inexplicable phenomena is celebrated as an essential component of mathematical philosophy and discovery. Consider the totient function, one of the most fundamental tools in number theory, which counts the positive integers up to a given number that are relatively prime to it, and imagine asking a deceptively simple question that has haunted mathematicians for over a century. Does there exist a composite number whose totient value divides the number -1 in the same way that the totient of every prime number does? This is Lamer's totient problem, named after Derek Henry Lamer, who posed it in 1932, and it represents a peculiar gap in our understanding of numbers that seems to hide just beyond the reach of our most powerful analytical tools. The problem asks whether any composite number can satisfy a specific divisibility condition that appears to be an exclusive privilege of primes, and despite enormous computational efforts and theoretical advances, no such composite number has ever been found, yet no proof of its non-existence has materialized either. The psychological mechanism at work here involves our deep intuition that mathematical properties should have clear boundaries and definitive answers. Yet Lamer's problem sits in an uncomfortable middle ground where decades of negative computational evidence have never crystallized into rigorous proof. We have checked billions upon billions of composite numbers, running algorithms that would have seemed impossibly sophisticated mere decades ago, and none has violated the expected pattern, yet the absence of evidence remains distinct from evidence of absence in the mathematical sense. This persistence without resolution stems from the peculiar difficulty of the number-theoretic structures involved, where the totient function and its interactions with multiplicative properties resist the standard proof techniques that have conquered so many other problems in this field. Consider the peculiar landscape of number theory, where mathematicians have long pursued patterns and properties that seem to govern the integers themselves. And within this realm exists a conjecture proposed in 1950 by an Italian mathematician named Giuseppe Giuga that remains tantalizingly unproven despite decades of computational verification and theoretical investigation. The conjecture states something deceptively simple, that if the sum of all divisors of a positive integer, excluding the integer itself, when multiplied together in a specific way, produces a particular remainder when divided by that integer, then that integer must be prime, which is to say it can only be divided evenly by 1 and itself. This means that Giuga believed he had discovered an entirely novel characterization of prime numbers, those fundamental building blocks of arithmetic that have captivated mathematicians since antiquity, and that this characterization would provide an elegant test for primality that worked in the opposite direction from how we typically think about checking whether a number is prime. What makes this conjecture simultaneously beautiful and maddening is that it has been verified computationally for every integer tested up to extraordinarily large values, yet no one has managed to prove it must always be true in general, nor has anyone found a counterexample that would definitively prove it false. The mechanism underlying why this conjecture has resisted proof for so long rests partly on the deeply recursive nature of number theory itself, where the properties of divisors and remainders become increasingly complex as numbers grow larger, and the tools available to mathematicians simply have not yet penetrated this particular veil with sufficient clarity. Consider the peculiar landscape of cubic equations and their integer solutions, where mathematician Marshall Hall proposed in 1955 a deceptively simple observation that has eluded proof for nearly 7 decades. If you take any two distinct integers, cube them both, and then subtract one result from the other, the absolute difference between these cubes will never equal exactly 2. This means that for any integers x and y where x does not equal y, the expression x cubed minus y cubed will never produce a value of 2, and remarkably, no one has been able to definitively prove this seemingly obvious claim, despite the fact that computational verification has checked billions upon billions of possible cases without finding a single counterexample. The conjecture emerges from a deep investigation into how cubic numbers relate to one another along the number line, revealing gaps and spaces that appear to follow invisible rules we can sense, but cannot articulate with mathematical certainty. When we examine consecutive cubes, the difference between 1 cubed and 2 cubed is 7, between 2 cubed and 3 cubed is 19, between 3 cubed and 4 cubed is 37. We observe that these gaps grow increasingly larger and follow a predictable pattern based on algebraic expansion, yet the specific claim that no two cubes differ by precisely 2 has resisted all attempts at logical containment. Mathematicians have developed increasingly sophisticated techniques, exploring the problem through number theory, algebraic geometry, and computational methods. And while these approaches have narrowed the possibilities and revealed structural constraints that make such an occurrence seem implausible, none have successfully closed the logical gap between intuition and proof. We have normalized this strange limbo of mathematical reality, where something appears abundantly true yet remains technically unverified, existing in a twilight space between established fact and conjecture, a reminder that even in the most precise of disciplines, certainty remains sometimes frustratingly elusive. Consider the infinite landscape of positive integers stretching endlessly before us, and within this realm exists a peculiar mathematical claim that has eluded proof for nearly a century, whispered about in academic corridors, yet remaining fundamentally unresolved. Pillai's conjecture, named after the Indian mathematician Subbiah Sivasankaranarayana Pillai, who proposed it in 1931, concerns itself with a deceptively simple question about the differences between consecutive factorial numbers and prime powers. Specifically, the conjecture asserts that for any positive integer k, the equation n factorial minus p to the power m equals k, where p represents a prime and m represents a positive integer, has infinitely many solutions across all possible values of k. In other words, no matter which positive integer you select, you should theoretically be able to express it as the difference between some factorial and some prime power. And you should be able to do this infinitely many times using different factorials and different prime powers. The conjecture operates in that shadowy frontier where number theory intersects with seemingly incomprehensible patterns, where mathematicians find themselves unable to determine whether this principle is absolutely true or whether counterexamples might exist that devastate the entire framework. What makes Pillai's conjecture psychologically fascinating is how it represents humanity's compulsion to find universal principles connecting disparate mathematical objects, as though the universe itself must exhibit harmony and completeness rather than gaps and exceptions. Mathematicians have verified the conjecture computationally for vast ranges of integers, accumulating evidence that strengthens intuitive belief in its validity. Yet this computational verification provides no actual logical proof that the pattern continues forever into the infinite. Imagine standing before a vast mathematical landscape where the fundamental relationships between numbers and their transcendental counterparts remain shrouded in mystery. A conjecture proposed by Stephen Schanel in 1966 that attempts to describe the algebraic independence of exponential functions in ways that mathematicians still cannot definitively prove or disprove. The conjecture essentially suggests that if you take any finite number of complex numbers that are algebraically independent over the rationals, then the transcendence degree of certain combinations of these numbers and their exponentials should follow a predictable pattern. Yet this seemingly reasonable expectation has resisted rigorous proof for nearly 6 decades despite being embraced as likely true by the mathematical community. The psychological mechanism underlying our acceptance of Schanel's conjecture rests on its elegant simplicity and its deep connection to other unsolved problems in transcendental number theory, creating a sense that it must be correct because it explains so many phenomena and aligns so perfectly with what mathematicians expect the universe of numbers to be, much like how we trust a perfectly constructed architectural blueprint even before construction begins. What makes Schanel's conjecture particularly fascinating in its unresolved state is how it illuminates the gaps in our understanding of basic mathematical objects like logarithms and exponential functions that we use constantly in applied mathematics and physics. And yet the most fundamental questions about their algebraic properties remain locked behind walls we cannot penetrate. We have normalized this conjecture into our working assumptions, building entire frameworks of number theory upon the assumption that it is true, citing it in proofs and using its consequences as foundations for further research, despite the fact that we lack the logical certainty required to call it proven, creating a peculiar mathematical culture where we collectively agree to treat an unproven statement as though it forms solid ground beneath our intellectual edifice. Imagine standing in a vast library where every book contains an infinite sequence of numbers, and you are tasked with finding patterns that should theoretically exist but remain perpetually hidden from view. This is the essence of the Littlewood Conjecture, a deceptively simple yet profoundly mysterious statement about the behavior of rational approximations to real numbers that has eluded proof for nearly a century. The conjecture proposed by the British mathematician John Littlewood in the early 20th century asserts that for any two irrational numbers, you can always find infinitely many pairs of integers such that when you multiply the distances from each irrational number to its nearest rational approximation, the product becomes arbitrarily small, approaching zero as you venture deeper into the infinite sequence of possibilities. The psychological mechanism that makes this conjecture so compelling rests on our intuition about randomness and distribution. It feels as though nature should allow us to simultaneously approximate two unrelated irrational numbers with extraordinary precision, yet the mathematical landscape stubbornly refuses to guarantee what our instincts insist should be true. Despite decades of rigorous investigation by the world's finest mathematicians, no counterexample has emerged to disprove the conjecture, nor has anyone managed to construct an elegant proof that would settle the matter definitively, leaving us in a state of mathematical limbo where the conjecture appears to be true everywhere mathematicians have looked, yet remains frustratingly unproven in its full generality. What persists is our acceptance of this uncertainty, our willingness to build upon assumptions about a statement we cannot verify, treating the Littlewood conjecture as a kind of mathematical foundation, even while acknowledging the fundamental ground beneath it may not be as solid as we hope, embodying the curious position that mathematics occupies between absolute certainty and perpetual doubt. Imagine a polynomial, that elegant mathematical function defined by coefficients and powers, and imagine that you have carefully located all of its roots, those precise points where the function equals zero on the complex plane. Now consider a circle drawn around each of these roots, a small circular boundary with a radius of exactly 1 unit, and ask yourself a deceptively simple question. Must there exist at least one critical point of this polynomial within or on the boundary of every single one of these circles? This is the essence of Sendov's conjecture, a problem posed by the Bulgarian mathematician Blagovist Sendov in 1959, which asks whether the critical points of a polynomial, the locations where its derivative vanishes, must necessarily cluster near the roots themselves. The conjecture appears almost self-evident when you consider it intuitively, for critical points represent the peaks and valleys of the function's landscape, and one might reasonably expect that the dramatic changes of direction captured by these critical points would occur in close proximity to the zeros where the function's graph crosses the horizontal axis. Yet despite this intuitive appeal, and despite more than 60 years of mathematical investigation, the conjecture remains unproven in its full generality, though mathematicians have successfully verified it for polynomials up to a certain degree and have established partial results that hint at its truth without confirming it absolutely. The psychological mechanism underlying our belief in Sendov's conjecture stems from a deeply human tendency to expect coherence and clustering in mathematical structures, an assumption that related phenomena should concentrate together rather than scatter randomly, and our confidence in this principle has been reinforced repeatedly by countless verified examples that seem to support the conjecture's claims. Deep within the realm of polynomial mathematics lies a deceptively simple yet profoundly unsolved question that has haunted mathematicians since 1993, when the Spanish mathematician Antonio Casas-Alvero first posed it to the mathematical community. The conjecture concerns itself with univariate polynomials, those elegant expressions consisting of a single variable raised to various powers and combined with coefficients, and it asks something that sounds almost trivial until one truly attempts to prove it. Imagine you have a polynomial of degree n, a function that behaves in a very specific mathematical way, and then imagine examining its derivatives, those functions that describe the rate of change of the original polynomial at every point. The Casas-Alvero conjecture proposes that if the original polynomial and all of its successive derivatives share a common root, a single value that makes each and every one of these functions equal to 0, then the polynomial must be a power of a linear polynomial, meaning it can be expressed as the same simple linear expression multiplied by itself many times over. This seems almost obvious intuitively, yet no mathematician has been able to prove it rigorously or find a counterexample that definitively disproves it. The conjecture has become one of those mathematical irritants that refuses to yield to conventional proof techniques, resisting attacks from algebraic geometry, complex analysis, and combinatorial approaches alike. Despite its apparent simplicity and numerous attempted proofs, the conjecture remains stubbornly unresolved, existing in that frustrating middle ground where it is neither proven true nor demonstrated false, leaving mathematicians in a state of perpetual uncertainty about whether they are pursuing a fundamental truth or chasing an illusion that may not even be correct. Imagine you are standing in a vast mathematical landscape where polynomials behave like functions that map points from one space to another, and you are trying to determine whether a particular transformation is reversible, whether you can always find your way back to where you started. The Jacobian Conjecture, posed by Otto Heinrich Keller in 1939, presents exactly this scenario, asking whether a polynomial map from multidimensional space to itself that has a non-zero Jacobian determinant everywhere must necessarily be injective, meaning it maps each input to a unique output with no collisions or overlaps. The conjecture seems almost self-evident at first glance, a mathematical common sense that should resolve itself through straightforward logic, yet it has resisted proof for more than 80 years despite the efforts of thousands of mathematicians across multiple continents and generations. The psychological mechanism underlying this persistence lies in the profound gap between our intuition about local behavior and global behavior, between what we can verify in small neighborhoods and what must be true across an entire infinite space. When the Jacobian determinant is non-zero at a point, the mathematics tells us that locally near that point, the transformation behaves like a linear map that is reversible, creating a sense of confidence that this property should extend everywhere. Yet somehow, impossibly, this local invertibility does not automatically guarantee global invertibility, and mathematicians have constructed increasingly complex counterexamples and near misses that suggest the conjecture might actually be false, or if true, requires insights from realms of mathematics we have not yet discovered. The conjecture has become normalized in the mathematical community as one of those perpetual mysteries, a fundamental question that hangs in a strange limbo where it is neither proven nor disproven, neither clearly true nor demonstrably false, existing in a state of mathematical uncertainty that defies the logical expectation that such a concrete yes or no question should eventually yield a definitive answer. Consider the landscape of linear operators in mathematics, those abstract machines that transform infinite dimensional spaces while preserving their essential structure, and imagine searching for a needle that might not exist in a haystack that stretches endlessly in directions your mind cannot fully visualize. The invariant subspace problem asks a deceptively simple question that has haunted functional analysis for nearly 70 years. Given any bounded linear operator on a complex Banach space, must there always exist a non-trivial closed subspace that remains unchanged when the operator acts upon it, a mathematical sanctuary where the transformation loops back into itself? This question emerged from the work of mathematicians seeking to understand the deepest properties of infinite dimensional spaces, those strange worlds where intuition fails and conventional geometry becomes almost meaningless, and it represents one of the most elegant formulations of our profound ignorance about the structures underlying higher mathematics. The psychological mechanism that makes this problem so captivating lies in its fundamental asymmetry. For finite dimensions, the answer is definitively yes. Every operator must have invariant subspaces, yet in the infinite realm, despite countless attempts by brilliant minds armed with increasingly sophisticated techniques, no one has ever proven this must remain true, nor has anyone produced a concrete counterexample that would shatter this expectation. We have normalized this uncertainty by compartmentalizing it into specialized subdisciplines where only experts dare venture, by accepting that some questions simply exceed our current mathematical capacity, much the way we accept that certain mysteries of quantum mechanics or consciousness remain beyond our grasp, and yet the problem persists in its elegant simplicity. A standing invitation to either genius or futility that continues to attract ambitious mathematicians who sense that solving it might reveal something fundamental about the nature of mathematical truth itself. Imagine standing in a vast forest where every tree possesses a hidden numerical identity, a labeling system so elegant and precise that mathematicians have spent decades trying to prove it must exist universally, yet remain unable to confirm this seemingly obvious truth. The graceful tree conjecture emerges from graph theory, a realm where trees are not organisms but rather networks of connected points, and the question at its heart is deceptively simple. Can every tree be labeled with numbers in such a way that each connection between points carries a unique difference? When we think about organizing information or mapping relationships, we instinctively believe that efficient, non-overlapping systems should always be possible, that nature and mathematics should align to reward our logical expectations with elegant solutions. The conjecture posits that for any tree structure with n vertices, we can assign the numbers 0 through n-1 to each point such that the absolute difference between connected points yields every integer from 1 to n-1 exactly once. And this labeling scheme has been called graceful because of its apparent perfection and symmetry. Mathematicians have verified this property for countless specific trees, for trees with particular shapes and sizes, and for infinite families of tree structures, building an almost overwhelming body of evidence suggesting the conjecture must be universally true. Yet despite this mountain of verification, despite the computational power brought to bear on the problem across decades, the general proof remains elusive, floating just beyond our grasp like a mathematical mirage. We have normalized this strange limbo where something demonstrably works in every observable case, where the evidence feels almost conclusive, yet where formal proof continues to elude even our most sophisticated mathematical minds, and we accept this paradox as simply another mystery that reminds us how much territory remains unexplored in the landscape of mathematical truth. Imagine you are holding a collection of photographs, each one showing a different view of a single building from various angles and distances, and your task is to determine whether these photographs alone are sufficient to reconstruct the original structure in its entirety, whether you could take every single image and use them to build back the three-dimensional form that existed before the camera captured it. And this is precisely the essence of what mathematicians call the Reconstruction Conjecture. A deceptively simple question posed in 1941 that has resisted resolution for more than 80 years, despite the combined efforts of some of the world's most brilliant minds. The conjecture concerns graph theory, which is the mathematical study of networks and connections, and it proposes that if you take any graph, which is essentially a collection of points called vertices connected by lines called edges, and you remove one vertex at a time to create what are called subgraphs, then knowing all of these individual subgraphs should theoretically allow you to reconstruct the original graph completely. As though you possessed a complete blueprint of something by knowing every partial view of it. The psychological mechanism that makes this conjecture so compelling is that it mirrors our intuitive understanding of reconstruction itself. The notion that sufficient partial information must necessarily contain enough data to recover the whole, that you cannot truly lose information by examining pieces individually if you examine all the pieces, and this seems almost tautological in its logic, almost impossible that it could be otherwise. Yet the conjecture remains unproven despite countless attempts, and despite its verification in special cases involving graphs with thousands of vertices. Imagine standing before a vast network of roads, railways, and interconnected pathways that stretch across an entire landscape, a system so intricate that tracing every possible route becomes a bewildering exercise in complexity. The cycle double cover conjecture emerges from this conceptual territory, representing one of graph theory's most perplexing and elegant puzzles that has resisted definitive proof for decades despite its deceptively simple statement. At its core, the conjecture proposes that every bridgeless graph, meaning any connected network without edges whose removal would disconnect the structure entirely, can be covered by a collection of cycles in such a way that each edge appears in exactly two of these cycles. like overlapping loops weaving through the entire structure with perfect mathematical symmetry. The psychological mechanism underlying this conjecture's persistence lies in our intuitive belief that mathematical systems possess a fundamental elegance and completeness that we struggle to articulate but deeply sense should exist. The conviction that graphs should possess this property without ever having proven it universally true. When we observe the cycle double cover property manifesting across countless specific graphs we can construct and verify, our minds experience a curious confirmation bias where the absence of a counterexample feels somehow like evidence of universal truth, even though the mathematical universe has repeatedly taught us that absence of evidence is not evidence of absence. We have normalized the uncertainty surrounding this conjecture through academic discourse and published papers that examine it from countless angles, each approaching it like detectives circling a crime scene without ever quite locating the pivotal clue that would unlock everything. And somehow this normalized state of incomplete understanding has become acceptable within mathematical culture, as if struggling toward an answer for 50 years constitutes a form of resolution in itself. Imagine you are holding a complex three-dimensional shape, perhaps something intricate and branching like a tangle of interconnected tubes, or a lattice structure that seems to fold back on itself in ways that challenge your spatial intuition. And you wonder how many smaller copies of this exact same shape you would need to assemble together in order to reconstruct the original. This deceptively simple question lies at the heart of the Hadwiger Conjecture, a problem that has perplexed mathematicians since Hugo Hadwiger proposed it in 1957, remaining stubbornly unresolved despite being stated with such apparent clarity that a student might initially believe it should yield to straightforward reasoning. The conjecture proposes that any shape or geometric object more formally known as a convex body in three-dimensional space can be covered by a finite number of smaller copies of itself, and specifically that in 3 dimensions no more than 8 such copies should ever be necessary, while in 2 dimensions 4 copies suffice, and in 4 dimensions 16 would be required, following a pattern of 2 raised to the power of the dimension. What makes this problem so deeply unsettling to contemplate is that while the conjecture remains unproven in dimensions higher than 3, mathematicians have verified it for countless specific cases and have developed intuitions suggesting it should be true. Yet no one has managed to construct a rigorous proof that applies universally across all possible shapes and dimensions. The psychological puzzle here involves our expectation that problems phrased in such elementary language, without reference to advanced calculus or abstract algebra, should respond to direct assault. Yet instead this conjecture has acquired a reputation for resisting every approach, becoming almost legendary in mathematical circles as a problem that seems like it should be simple, but reveals unfathomable depths the moment you attempt engagement with its structure. Imagine standing before a vast network of pipes, some flowing with water, others empty, all connected in an intricate web where certain junctions must receive precisely the amount of liquid they demand, and certain pipes can only carry a maximum capacity without bursting, and your task is to route the flow efficiently from sources to sinks while respecting every constraint. This is the essence of the maximum flow problem, a foundational concept in network theory that has occupied mathematicians and computer scientists for decades. Now consider that within this same network exists something called a cycle cover, a collection of circular paths where every pipe in the network appears in exactly one cycle, creating a decomposition of the entire structure into these loops. The Burge-Fulkerson conjecture, proposed in 1955, makes a deceptively simple claim that for any cubic graph, a graph where every vertex has exactly 3 connections, there exists a collection of 6 perfect matchings whose union covers every edge exactly twice. This conjecture sits at the intersection of graph theory and combinatorial optimization, describing a fundamental relationship between flow decompositions and matching theory that seems as though it should be provable, yet it resists proof with remarkable stubbornness. The psychological mechanism underlying our fascination with this problem lies in its elegant simplicity paired with its apparent inevitability. When mathematicians examined small cubic graphs, they found the conjecture held true universally, creating the sense that this must be a fundamental law of graph structure rather than a mere coincidence. We have become accustomed to accepting its truth despite its unproven status, building dependent theories upon it, and incorporating it into our intuitions about how networks must behave. Deep within the landscape of graph theory and combinatorics exists a deceptively simple proposition known as Barnett's conjecture, named after the mathematician David W. Barnett, who formulated it in 1969, and it concerns itself with the properties of planar graphs, those mathematical structures that can be drawn on a flat surface without edges crossing one another in ways that would violate certain fundamental properties. The conjecture suggests that every three-connected cubic planar graph, which is to say every planar graph where each vertex connects to exactly three edges and removing any two vertices leaves the graph still connected, must be Hamiltonian, meaning there exists within it a cycle that visits every single vertex precisely once and returns to the starting point. This seems intuitively reasonable, almost self-evident in its plausibility, yet despite decades of intense mathematical investigation and computational verification across increasingly complex examples, the conjecture has resisted all attempts at rigorous proof, remaining tantalizingly suspended between assumed truth and demonstrated reality. What makes Barnett's conjecture particularly fascinating is how it occupies this peculiar space in mathematical consciousness, where it has been verified computationally for graphs with hundreds of thousands of vertices, generating an overwhelming empirical case for its validity. Yet the logical pathway to an actual proof remains obscured behind conceptual barriers that mathematicians have been unable to penetrate. The psychological mechanism underlying our relationship with this conjecture involves a fascinating tension between the weight of evidence on one hand and the requirement for absolute certainty on the other, creating a scenario where we know something appears to be true with near universal consistency across all tested cases. Yet we cannot articulate why this must be true in all possible cases without exception. Imagine a vast network of directed pathways where every single node, every intersection point in this intricate web, has at least one outgoing connection to somewhere else within the system. Yet despite this seemingly simple constraint, mathematicians cannot determine with certainty whether every node can reach another node within a bounded distance. The Kakeya Conjecture, formulated in 1978, proposes that in any directed graph where every vertex has outgoing degree at least 1, there must exist a directed cycle of length at most equal to the total number of vertices divided by the minimum degree requirement, a statement so elegant in its formulation that it appears almost self-evident, yet it has resisted proof for over 4 decades. The conjecture emerged from a simple observation about the structure of directed networks, where the researchers wondered whether the density of outgoing connections must inevitably force the existence of short cycles, creating loops that circle back upon themselves within predictable distances. What makes this conjecture psychologically compelling is the intuitive sense that forcing every point to connect outward should severely restrict the possible configurations, creating inevitable bottlenecks and forcing paths to collide with themselves. Yet mathematicians have discovered that networks can be arranged in unexpectedly clever ways that postpone or seemingly evade these forced cycles. The conjecture remains unproven despite significant efforts from graph theorists, with partial results confirming it under additional constraints or for specific types of directed graphs, while counterexamples that would disprove it have never been found, creating a peculiar liminal space where mathematicians operate with high confidence in its truth while remaining unable to establish it rigorously. Consider a directed graph, a mathematical structure where points connect to one another through arrows indicating direction and relationship, and within this abstract landscape exists a conjecture posed by Paul Seymour in 1974 that remains unproven to this day, concerning what mathematicians call the second neighborhood of any given vertex in such a directed graph. When you select any single point within this network, you can identify its first neighborhood as all the points that connect outward from it, the immediate descendants following the arrows, and then you might reasonably expect to also identify a second neighborhood, perhaps those points reachable in 2 steps forward, or those points that connect to your selected point's outgoing neighbors. Yet Seymour's conjecture proposes something stranger and more elusive. That in any directed graph without certain problematic structures, every vertex must have a second out-neighborhood at least as large as its first out-neighborhood, meaning the number of vertices reachable through your initial connections should be matched or exceeded by vertices reachable in an additional step, a claim that feels almost tautological in its simplicity, yet refuses to submit to proof despite decades of mathematical effort. The psychological mechanism underlying our difficulty in resolving this question stems from the gap between intuitive graph behavior and rigorous proof, where examples seem to support the conjecture perfectly, lending us a false confidence that the principle must be universal. Yet when mathematicians attempt to construct a formal argument that covers all possible graph configurations without exception, they discover that each approach contains a subtle vulnerability, a hidden case that their logic fails to encompass. Consider a map or a network of intersecting lines and points, where you must assign colors to both the edges and the vertices in such a way that no two adjacent elements share the same color, and no vertex shares a color with any of its incident edges, creating a complete chromatic separation across the entire structure simultaneously. The total coloring conjecture, proposed in 1964 by mathematicians working independently on the problem, suggests that for any simple graph, you need at most delta plus 2 colors to accomplish this seemingly impossible task, where delta represents the maximum degree of any vertex in that graph. The conjecture appears almost modest in its claim, a mere 2 colors beyond what intuition might first suggest necessary, yet despite nearly 6 decades of mathematical scrutiny from some of the world's most brilliant minds, no one has managed to prove it holds universally, nor has anyone discovered a counterexample that definitively proves it false. The psychological mechanism underlying our obsession with this problem stems from our fundamental human need to organize chaos, to establish order through systematic classification, and the total coloring conjecture represents an elegant expression of this desire applied to abstract mathematical structures. What makes this conjecture particularly maddening is that it has been verified computationally for graphs of impressive size and complexity, and it has been proven true for specific classes of graphs with special properties, yet the universal truth remains tantalizingly beyond our reach, suspended in a liminal space between proven and disproven. We have normalized the existence of this unresolved question, teaching it in universities and research institutions as simply another frontier in mathematical knowledge, treating the uncertainty not as a failure of mathematics, but as an indication of genuine depth and difficulty within the discipline itself. In the heart of combinatorial mathematics lies a deceptively simple yet profoundly puzzling question that has occupied the minds of some of the world's most brilliant researchers for decades. A question that asks us to consider the nature of pattern and repetition in abstract mathematical structures. The sunflower conjecture, first articulated formally by Paul Erdos and Richard Rado in 1960, concerns itself with the existence of certain configurations within finite sets, specifically asking whether every sufficiently large collection of sets must necessarily contain what mathematicians call a sunflower, which is a collection of sets that share a common intersection while their pairwise differences remain completely disjoint from one another. To visualize this concept, imagine a garden of flowers where each petal represents a unique element and the center represents the shared kernel, with the remarkable property that no two petals share any elements with one another outside of that central core. The conjecture asserts that no matter how we arrange collections of sets, if we gather enough of them together, this sunflower pattern will inevitably emerge, like a botanical truth woven into the fabric of mathematical reality itself. What makes this conjecture so deeply unsettling is that it appears almost self-evidently true, yet no one has successfully proven it in its full generality, despite more than 6 decades of sustained effort from mathematicians working across multiple continents and generations. The psychological mechanism underlying our fascination with this problem stems from the gap between intuitive certainty and rigorous proof, the strange vertigo we experience when something feels obviously true yet stubbornly resists formal demonstration. Researchers have managed to prove special cases and variations, establishing partial results that suggest the conjecture should be true, and yet the complete universal statement remains frustratingly beyond reach. Imagine a graph, that abstract mathematical object composed of vertices connected by edges, where every single vertex has an odd degree, meaning an odd number of lines emerging from each point, and imagine that mathematicians have been staring at these peculiar structures for decades, unable to prove or disprove a seemingly simple claim that Paul Erdos and Andras Jarfaz proposed, that within any such graph there must exist a cycle whose length is a power of 2, such as cycles of length 4, 8, 16, 32, or 64. The conjecture sits there in the mathematical landscape like an unsolved puzzle that refuses to yield despite the extraordinary efforts of countless researchers who have approached it from every conceivable angle, testing it against vast computational experiments, examining special cases, and developing increasingly sophisticated graph-theoretic machinery. The psychological mechanism underlying the persistence of this conjecture involves the human tendency to recognize patterns in nature and mathematics, and then to elevate those patterns into universal principles without being able to articulate precisely why they must hold true across all possible configurations. Mathematicians observe that powers of two appear throughout nature and mathematics with striking regularity, from binary systems to hierarchical structures, and this observation creates an intuitive conviction that such orderly progression should necessarily manifest within the constraints of odd-degree graphs. The conjecture has achieved a kind of institutional permanence, remaining unsolved yet continually relevant because it connects to fundamental questions about cycle structures in graphs, and despite possessing no logical barrier to resolution, it persists as one of those enigmatic problems that demonstrates how mathematical truth often resists our most earnest attempts at proof, reminding us that even in the most abstract domains of human thought, where all the rules are explicitly stated and nothing is left to ambiguity, mystery continues to flourish and elude our grasp with remarkable persistence. Imagine a collection of curves drawn on a flat surface, each one looping and twisting through space in ways that seem deliberately designed to complicate matters, and now imagine trying to understand the fundamental rules about how these curves must interact with one another based solely on the count of their crossings. This is the essence of the Thrackle Conjecture, a deceptively simple yet profoundly mysterious problem in graph theory that has resisted solution since its introduction in the 1960s by John H. Conway. A thrackle is defined as a graph drawn in the plane such that every pair of edges intersects exactly once, either at a shared endpoint or at a crossing point in the interior of the plane, and the conjecture proposes that any thrackle drawn on a flat surface can contain at most as many edges as it has vertices, a constraint that seems reasonable on its surface, but remains fundamentally unproven despite decades of mathematical investigation. The psychological appeal of this conjecture lies in its deceptive accessibility, for it can be understood by anyone with basic knowledge of graphs and intersecting lines, yet it hides layers of complexity that have eluded even the most sophisticated mathematical approaches, creating a peculiar cognitive dissonance where the statement seems almost obvious, yet proves stubbornly resistant to rigorous proof or disproof. Mathematicians have verified the conjecture for small cases and specific types of thrackles, building confidence in its truth, yet no general proof has emerged to settle the question once and for all, and this persistence of uncertainty despite apparent simplicity reflects how mathematics often normalizes the existence of fundamental gaps in our understanding, accepting that some problems resist elegant solutions even when they appear elementary at first glance. Consider the abstract mathematical landscape where points scatter across a plane, and imagine asking a deceptively simple question. If you place n points within a bounded region, what is the largest possible minimum area that must exist among all the triangles those points can form? This is the essence of the Heilbronn triangle problem, named after Hans Heilbronn, who posed it in 1946, and it remains one of mathematics' most frustratingly elusive puzzles despite decades of serious investigation by brilliant minds. The problem asks us to find the optimal configuration of points that maximizes the smallest triangle area they create, which means we are searching for an arrangement where even the tiniest triangle is as large as possible, a paradoxical optimization that forces us to think about balance and distribution in profoundly counterintuitive ways. Mathematicians have proven bounds on this problem, establishing that the minimum triangle area must decrease at some rate as we add more points. Yet the precise rate remains maddeningly uncertain, with proposed formulas that might decay logarithmically or polynomially, each with substantial evidence, yet neither conclusively proven. The psychological mechanism underlying our struggle with this problem stems from our intuition's failure when dealing with high-dimensional spaces and combinatorial explosion. For as the number of points increases, the number of possible triangles grows so rapidly that our mental models collapse under the weight of complexity. We expect that with clever arrangement, we should be able to control all triangle areas simultaneously. Yet the problem reveals a fundamental tension where spreading points to enlarge small triangles inevitably creates other constraints that prevent us from achieving the theoretical ideal we imagine. What persists most troublingly is our sense that the answer should be knowable, that some elegant configuration or mathematical principle should unlock this puzzle, yet we remain suspended in uncertainty, able only to narrow the boundaries of possibility without ever quite grasping the truth that may lie within. Imagine you are given a collection of straight lines arranged across a flat surface, and your task is to count how many non-overlapping triangles these lines can create through their intersections and boundaries. This is the essence of the Koban triangle problem, named after the Japanese artist Koban Fujimoto, who posed this deceptively simple question in the 1970s. The problem asks a fundamental question. If you have n straight lines in a plane, what is the maximum number of non-overlapping triangles that can be formed by their intersections? It seems like it should have a clean, elegant answer, some formula that scales predictably as you add more lines, yet mathematicians have discovered that the problem resists such simplicity in profoundly unexpected ways. When you add one line to your configuration, it does not simply add a fixed number of triangles. Instead, the relationship between lines and triangles becomes increasingly Byzantine and difficult to characterize. The human mind naturally expects optimization problems to follow clear hierarchical patterns, where adding resources linearly produces predictable outcomes, but the Koban triangle problem violates this intuition at every turn. Researchers have verified solutions for small numbers of lines through computational brute force, establishing that 4 lines can create at most 4 triangles, while 8 lines can create at most 20 triangles, yet no general formula has emerged to predict the maximum for arbitrary values of n. This absence of pattern creates a peculiar psychological discomfort. Because mathematicians have evolved to expect that sufficiently clever thinking will eventually reveal the underlying structure of any well-posed question. The problem persists in mathematical literature not because it is practically important for engineering or physics, but because it represents a category of combinatorial optimization problems where our intuitions about scaling and structure appear fundamentally unreliable, forcing us to confront the possibility that some elegant questions might require inelegant, case-by-case analysis rather than universal formulae. Consider the peculiar geometric puzzle that Ludwig Danzer posed to the mathematical community in the 1960s, a problem that asks whether there exists a finite set of tiles that can fill 3-dimensional space in only an aperiodic manner, meaning that no matter how you arrange these shapes, they refuse to create any repeating pattern that extends infinitely in any direction. This question emerges from the observation that in 2 dimensions, we have discovered aperiodic tile sets, most famously the Penrose tiles discovered in the 1970s, which create beautiful and intricate patterns that never repeat, yet their 3-dimensional counterpart remains stubbornly elusive and fundamentally uncertain. The psychological mechanism that makes this problem so vexing is our deep human intuition that structure and repetition should eventually emerge from any finite set of building blocks. Yet mathematicians have found repeated counterexamples to this expectation, forcing us to confront the reality that higher dimensional spaces behave in ways that defy our lower dimensional intuitions and experiences. What makes Danzer's problem particularly frustrating is that we cannot even definitively prove whether such an aperiodic tile set exists, or whether it is impossible, leaving mathematicians suspended in a state of profound uncertainty where the answer could swing either way, and both outcomes would fundamentally alter our understanding of how shapes and patterns behave in 3-dimensional space. We have normalized this uncertainty by incorporating it into our daily acceptance of unsolved problems, treating it as simply another fascinating riddle that humanity has not yet solved. Yet it represents something deeper about the limits of our geometric knowledge and the strange territory where 3-dimensional mathematics becomes genuinely alien to our intuitive understanding of how the universe organizes itself. In the realm of graph theory, there exists a deceptively simple concept that has haunted mathematicians for decades, a conjecture proposed by Vaclav C.H. Vattel that concerns itself with the structural resilience of graphs, specifically a measure known as toughness. Imagine a network of points connected by lines, and consider what happens when you begin removing points from this network. The question becomes not merely how many points you must remove, but rather the ratio between the number of points removed and the number of disconnected components that result from their removal. Toughness is precisely this ratio, a single number that quantifies how robust a network truly is, how resistant it remains to fragmentation. C.H. Vattel conjectured in 1973 that every graph possessing a Hamiltonian cycle, that is to say a path that visits every single point exactly once before returning to its starting location, must also possess a toughness value of at least 1/2. This seems like it should follow logically from the definition, and yet the conjecture remains unproven to this day, stubbornly resisting the efforts of brilliant minds across generations. The psychological mechanism at play here involves our tendency to conflate intuitive elegance with mathematical truth, to assume that properties which feel related must actually be connected through some deeper principle. And yet graph theory has repeatedly taught us that such assumptions mislead us. We have normalized this particular open question by simply accepting that some problems may require revolutionary new mathematical frameworks to solve, frameworks we have not yet invented, or perhaps insights so fundamental that they remain hidden in plain sight within the very definitions we use every day. Picture a sprawling industrial brick factory in early 20th century Hungary, where workers must transport bricks from one location to another across a vast, open yard, and the most efficient path between any 2 points would naturally seem to follow a straight line through the empty space. However, the factory contains several large storage sheds positioned seemingly at random throughout the grounds, and these buildings obstruct the direct routes, forcing workers to navigate around them in complex patterns that add considerable distance to each journey. This real-world logistical nightmare inspired the Hungarian mathematician Paul Ceran to formulate one of graph theory's most perplexing problems. How do you arrange a collection of points on a plane and connect them with lines in such a way that you minimize the number of times those lines must cross over one another? The underlying mechanism that makes this problem so intellectually resistant to resolution stems from the fundamental tension between two competing desires in geometric optimization: the urge to keep things simple and connected versus the inevitability that as complexity increases, crossings become nearly impossible to avoid entirely. What makes Ceran's problem particularly insidious is that we can easily verify when a solution is correct by counting the crossings, yet predicting the optimal arrangement before actually constructing it remains stubbornly elusive, and even with modern computational power, we find ourselves unable to determine the precise minimum number of crossings for moderately sized problems. The problem persists in contemporary mathematics not because anyone forgot about it or deemed it irrelevant, but rather because its fundamental difficulty reveals something unsettling about the nature of geometric optimization itself. That even problems we can state in simple terms may require exponentially greater effort to solve than we would intuitively expect, and that our intuitions about spatial arrangement fundamentally mislead us when scaled beyond the immediately visible world. Imagine you are standing before a piece of paper with several points marked upon it, and your task is to connect these points with lines in such a way that you create a complete graph, where every point connects to every other point without exception. And as you draw these connections, some of the lines must inevitably cross over one another in the middle of the paper. The crossing number problem asks a deceptively simple question that has haunted mathematicians for decades. What is the minimum number of times these lines must cross each other, given any particular number of starting points? This is not merely an abstract curiosity confined to the chalkboards of universities, but rather a question with profound implications for circuit design, network optimization, and the physical layout of computer chips, where every crossing represents a potential source of interference, delay, or manufacturing complexity. When engineers design the intricate pathways on a microchip or plan the routing of cables through underground conduits, they must grapple with this same fundamental constraint, because the fewer times their connections cross, the more efficient and economical their designs become. The psychological mechanism that makes this problem so persistently difficult to solve stems from our intuitive belief that geometry should offer us clean answers, that there should be a formula or pattern that elegantly determines the optimal arrangement for any configuration of points. Yet mathematics consistently refuses to provide such clarity. Despite centuries of effort and the involvement of some of the brightest minds in graph theory, we have not discovered a general formula for the crossing number of arbitrary graphs, and even for specific well-studied graphs, The exact crossing numbers remain unknown, existing somewhere in a frustrating liminal space between upper and lower bounds that we can calculate but never quite definitively prove. Consider the deceptively simple question that emerged from David Hilbert's famous 1900 list of unsolved mathematical problems. What is the maximum number of isolated closed curves that a polynomial equation can create when drawn on a plane, and how are these curves distributed relative to one another? This 16th problem seems almost trivial when first encountered, yet it has resisted complete resolution for more than a century, haunting mathematicians with its apparent simplicity masking profound complexity. The problem asks us to understand limit cycles in dynamical systems, which are closed trajectories that attract or repel nearby paths in the mathematical space, creating boundaries between regions of vastly different behavior. When you observe a pendulum swinging or watch the behavior of predator-prey populations cycling through time, you are witnessing the real-world manifestations of these invisible mathematical structures that Hilbert's question attempts to enumerate and constrain. The psychological mechanism underlying our difficulty with this problem stems from the fact that while we can create polynomial equations of arbitrarily high degree, each increase in complexity seems to permit new cycles that our intuition cannot predict or bound, creating an ever-receding horizon of understanding that defies our attempts to establish universal rules. We have developed partial answers in special cases, establishing bounds for low-degree polynomials and creating sophisticated tools from complex analysis and topology to probe the problem's structure. Yet we have somehow normalized this incomplete state as acceptable mathematics, allowing Hilbert's 16th problem to persist in a curious liminal space where we understand much but lack the complete picture. Much as we accept that certain fundamental questions about nature may never yield to complete resolution despite our best theoretical efforts. In the field of algebraic geometry, there exists a deceptively simple assertion about polynomial rings and their geometric counterparts that has eluded proof for more than half a century. A conjecture posed by the Japanese mathematician Masayoshi Nagata in 1959 that concerns itself with whether certain seemingly fundamental properties of polynomial rings must necessarily hold true under specific conditions. The conjecture emerges from deep within the intersection of commutative algebra and algebraic geometry, two disciplines that attempt to understand the structure of polynomial equations and the geometric shapes they represent, and it specifically addresses the question of whether a finitely generated algebra over a field must possess a particular property related to its dimension and the way it sits within larger algebraic structures. The core mechanism underlying this conjecture involves the relationship between an algebra's abstract algebraic properties and its tangible geometric interpretations, a bridge that mathematicians have long sought to understand fully, yet somehow this particular bridge seems to have a fundamental plank missing that no one has quite managed to locate or construct. Despite decades of intense scrutiny from some of the world's most brilliant minds in pure mathematics, despite the development of sophisticated tools and techniques that have solved countless related problems, Nagata's conjecture remains stubbornly impervious to proof, resisting attacks from multiple angles and perspectives. Imagine standing before an infinite landscape of numbers arranged along a horizontal line, each one representing a zero of the Riemann zeta function, one of mathematics' most enigmatic objects, and imagine that mathematicians have observed a peculiar pattern emerging from this wilderness of values. Every zero they have ever found appears to lie perfectly on a single vertical line, as if some invisible force were constraining these numbers to a specific boundary, like a fence running through an infinite field that refuses to be crossed. The Hilbert-Palya conjecture proposes that this is no accident, that there exists a deeper mathematical structure, perhaps some hidden physical operator or quantum mechanical principle, that explains why these zeros behave with such remarkable uniformity and discipline. For over a century, despite the combined efforts of the world's greatest mathematicians and computer scientists, who have now verified this pattern for trillions upon trillions of zeros, the underlying reason for this order remains profoundly mysterious and inaccessible to proof. The conjecture emerges from the observation that the Riemann hypothesis, which asserts that all non-trivial zeros must lie on this critical line, appears to be true in every single case ever examined, yet no one has successfully demonstrated why this must be universally true, creating a peculiar situation where the evidence is overwhelming, but the logical foundation remains elusive and out of reach. What makes this conjecture particularly haunting is that several mathematicians, including Hilbert himself and later Palea, have speculated that if one could construct or discover the right mathematical or physical framework, something akin to an eigenvalue problem in quantum mechanics, then the zeros would automatically fall into place, like pieces of a puzzle that have always belonged together, but whose assembly instructions have been lost to time. Deep within the architecture of mathematics lies a conjecture so vast and pervasive that its truth or falsity would reshape our understanding of number theory itself. And this is the generalized Riemann hypothesis, a sweeping extension of one of the most famous unsolved problems in all of mathematics. The original Riemann hypothesis, posed in 1859, concerns the zeros of a specific function called the Riemann zeta function, which encodes the distribution of prime numbers within the natural integers, and Riemann proposed that all non-trivial zeros of this function lie on a single vertical line in the complex plane, a deceptively simple statement that has resisted proof for nearly 2 centuries. The generalized Riemann hypothesis takes this idea and expands it dramatically, suggesting that not only does the Riemann zeta function exhibit this orderly behavior, but that vast families of similar functions called Dirichlet L functions and even more general mathematical objects all obey the same fundamental principle, that their zeros cluster along specific mathematical lines in a pattern of almost supernatural regularity. What makes this hypothesis so compelling and so frustrating is that mathematicians have verified it for trillions upon trillions of cases through computational means. Yet computational verification, no matter how extensive, can never constitute a proof, and the gap between evidence and certainty remains unbridgeable through empirical methods alone. The psychological mechanism behind our obsession with this problem stems from the human recognition that, if true, the generalized Riemann hypothesis would imply profound constraints on how number theory operates at its deepest levels, revealing hidden structures and symmetries that govern the behavior of prime numbers across all mathematical domains. Imagine standing before an infinite landscape of numbers stretched across an invisible plane, where each point represents a mathematical truth that either aligns with a perfect invisible line or deviates into chaos. And the question of whether every single one of these infinitely many points obeys the same hidden rule has haunted mathematicians for nearly 2 centuries without resolution. The Riemann hypothesis, proposed in 1859 by the German mathematician Bernhard Riemann, concerns the distribution of prime numbers and their deepest structural properties, encoded within an enigmatic function whose zeros seem to arrange themselves along a single straight line through complex space. Yet nobody has ever proven this to be universally true. The hypothesis suggests that all non-trivial zeros of the Riemann zeta function possess a real part equal to 1/2, a remarkably specific claim that would unlock profound understanding about how primes scatter among the natural numbers. Yet despite countless computational verifications confirming billions upon billions of individual cases, the general proof remains perpetually out of reach. What makes this problem psychologically fascinating is how it represents the human encounter with infinity itself, for we can verify the pattern holds true for every zero we can calculate with our most powerful computers, yet this verification approaches infinity like a person walking toward the horizon, never arriving at the destination, but seeing only more landscape unfold. The mathematical community has essentially normalized the unproven status of the Riemann hypothesis by building entire frameworks of modern mathematics upon its assumed truth, creating an elaborate conditional architecture where if the hypothesis were to fail at some distant point, countless downstream theorems and cryptographic systems would crumble into uncertainty. The Tate conjecture stands as one of the most profound unsolved problems in algebraic geometry and number theory, formulated by the mathematician John Tate in 1963, and it concerns the fundamental relationship between two vastly different mathematical structures that seem to have no reason to be connected at all. At its core, the conjecture proposes a deep correspondence between algebraic cycles on algebraic varieties and something called Galois representations, which are abstract mathematical objects that encode symmetries of number fields. And this correspondence suggests that certain geometric properties of shapes defined by polynomial equations should align perfectly with these purely algebraic symmetries in a way that appears almost miraculous, given how differently these two domains were originally developed and conceived. The psychological mechanism that makes this conjecture so peculiar and unsettling is that mathematicians have discovered empirical evidence suggesting this connection holds true in numerous specific cases. Yet we possess no overarching framework or logical pathway that explains why the universe of mathematics should organize itself in such a harmonious way. As though two completely separate languages are somehow translating each other with perfect fidelity despite being constructed from entirely different vocabularies and grammatical rules. What makes the Tate conjecture persist in this state of fascinating uncertainty is precisely the fact that partial verifications have emerged across various mathematical contexts, providing tantalizing hints that something profound is being glimpsed. Yet these pieces of evidence remain scattered and incomplete, never coalescing into a comprehensive proof that would resolve the underlying mystery once and for all. Imagine standing in a vast cathedral of mathematics where two entirely separate wings of human knowledge, number theory and harmonic analysis, have always been kept apart by towering walls of incompatibility, and yet somewhere in the architectural blueprint of reality. A visionary mathematician named Robert Langlands glimpsed the possibility that these two worlds might actually be connected by a hidden correspondence, so profound and intricate that it would require decades of collaborative effort across multiple generations of mathematicians to even begin to understand its full implications. The Langlands Program, proposed in 1967, represents one of the most audacious and bewildering conjectures in modern mathematics, suggesting that seemingly unrelated mathematical objects, Galois groups that describe symmetries of number fields, and automorphic forms that emerge from harmonic analysis, are actually manifestations of the same underlying reality viewed through different lenses. Yet this tantalizing possibility remains largely unproven despite being considered perhaps the most important unsolved problem in all of contemporary mathematics. What makes this puzzle psychologically destabilizing is that mathematicians have accumulated overwhelming circumstantial evidence supporting Langlands' vision. Fragments of the correspondence have been verified in special cases, entire subcategories of the program have yielded to proof, and yet the complete general framework continues to resist all attempts at comprehensive resolution, leaving researchers suspended in a state of profound intellectual uncertainty where the pattern seems undeniably real but remains fundamentally elusive and incomplete. Within the vast landscape of modern mathematics, there exists a peculiar collection of assumptions that have become so deeply embedded in the foundation of algebraic geometry and number theory that mathematicians often proceed with their research as though these conjectures were established fact, despite the absence of formal proof spanning decades or even centuries. The standard conjectures, formulated most notably by Alexander Grothendieck in the 1960s, represent a family of profound statements about the nature of algebraic cycles and their relationships to cohomology theory, predictions so fundamental that their truth or falsehood would reshape our understanding of how mathematical structures behave at their deepest levels. What makes this situation particularly fascinating from a logical perspective is that mathematicians worldwide have constructed elaborate theoretical frameworks, proven thousands of downstream results, and developed entire subfields of study that tacitly assume these conjectures hold true, even though no one has managed to demonstrate their validity with absolute certainty. The psychological mechanism at work here involves a kind of mathematical faith, where the internal consistency and aesthetic elegance of a conjecture become so compelling that researchers treat it as functionally equivalent to truth, building architectural towers of theorems upon foundations that remain unproven. This practice has become so normalized within academic circles that many working mathematicians can conduct their entire careers without ever directly engaging with the question of whether the standard conjectures themselves are actually true, instead focusing on deriving consequences from their hypothetical validity. The peculiar aspect of this normalization is how it persists despite representing a significant logical vulnerability, a collective agreement to ignore a fundamental epistemological gap in favor of mathematical productivity and progress, creating a situation where the assumptions have become more important than the truths they were meant to illuminate. Deep within the architecture of modern number theory lies a question so fundamental, yet so elusive, that mathematicians have spent decades circling around its implications without ever quite grasping its resolution. And this question concerns the nature of Galois representations and how they relate to the mysterious realm of modular forms. The Fontaine-Mazur conjecture, proposed in the 1980s by the mathematicians Jean-Marc Fontaine and Barry Mazur, asks whether every geometric Galois representation of a certain type must come from the cohomology of an algebraic variety, essentially questioning whether certain abstract algebraic structures that appear to describe fundamental symmetries of numbers must necessarily arise from concrete geometric objects we can somehow visualize or construct. The psychological mechanism at work here involves our deep human desire for unity and interconnectedness in mathematics, the sense that if two seemingly different mathematical objects exhibit the same patterns and symmetries, they ought to be manifestations of some deeper underlying reality that bridges their domains. When mathematicians work with Galois representations, which are mathematical objects that encode how the absolute Galois group acts on various algebraic structures, and when they separately study modular forms, which are highly symmetric functions with remarkable properties, they encounter what appears to be an inexplicable correlation between these two entirely different worlds, a correlation so consistent that it feels almost impossible that one should not deterministically determine the other. The section conjecture emerges from a peculiar observation within algebraic geometry, where mathematicians have noticed that certain geometric objects called algebraic varieties seem to possess sections or continuous selections that ought not to exist according to conventional reasoning, yet they persistently do appear when examined through particular theoretical frameworks. Imagine a complex mathematical landscape where you're attempting to find a continuous path or selection that respects the underlying structure of the space, much like trying to comb the surface of a sphere smoothly without creating any disruptions or singularities, except that in this case the sphere exists in multiple dimensions, and the act of combing itself becomes profoundly abstract and laden with hidden constraints. The conjecture suggests that under certain conditions related to the topology and arithmetic properties of these varieties, such sections should be guaranteed to exist, yet proving this remains tantalizingly beyond current mathematical reach, creating a situation where vast computational evidence supports the conjecture while theoretical proof remains elusive and fragmented. What makes this particularly vexing is that mathematicians can observe these sections appearing in specific cases and can even construct them explicitly in certain scenarios, which creates an almost paradoxical situation where the phenomenon seems entirely real and demonstrable, yet resists being captured within a unified theoretical framework that would work universally. The persistence of the section conjecture, despite the absence of a complete proof, reflects a deeper philosophical question about whether mathematics is discovering truths that already exist in some abstract realm, or whether mathematicians are essentially observing patterns that emerge from their own symbolic systems, patterns that appear consistent enough to warrant belief, yet remain fundamentally unprovable within established axioms. In the year 1984, the mathematician Paul Vogte proposed a conjecture that unifies several disparate areas of mathematics into a single grand framework, suggesting a profound connection between the geometry of algebraic varieties and the arithmetic properties of their rational points. Yet despite decades of research by some of the world's most brilliant mathematical minds, the conjecture remains stubbornly unproven and continues to resist all attempts at verification or falsification. The conjecture essentially posits that for any algebraic variety over a number field, the rational points that lie outside a proper closed subset become increasingly rare as one measures their height, which is a mathematical way of quantifying how complicated or large a rational number is, and this rarity should be quantifiable according to a precise inequality involving several intricate invariants from algebraic geometry. What makes Vogte's conjecture particularly elusive is that it functions simultaneously as a unifying principle that would explain why numerous other famous conjectures in mathematics, including Falting's conjecture and the Mordell-Lang conjecture, must be true, yet proving it remains fundamentally beyond our current mathematical apparatus and conceptual frameworks. The psychological mechanism that keeps mathematicians engaged with this problem, despite its apparent intractability, lies in the seductive elegance of the conjecture itself, for it suggests that mathematics contains an underlying architecture of astounding beauty and coherence, where seemingly unrelated phenomena are actually manifestations of a single principle. And this promise of unity drives researchers forward even when confronted with seemingly insurmountable technical obstacles. Consider the landscape of algebraic geometry, where mathematicians study the properties of geometric objects defined by polynomial equations, and imagine within this abstract realm a fundamental question about how often certain types of mathematical structures can exist. The Bombary-Lang conjecture, formulated in the late 20th century by Enrico Bombary and Serge Lang, proposes that a variety of general type defined over a number field contains only finitely many rational points, and furthermore that these rational points are not densely distributed, but rather sparse and isolated, confined to proper subvarieties of lower dimension. The conjecture addresses a deep tension within arithmetic geometry between the vastness of rational numbers and the restrictive properties of algebraic varieties, suggesting that high-dimensional geometric structures become increasingly impoverished when we restrict our attention only to solutions involving rational coordinates. This conjecture emerged from the natural human impulse to categorize and bound the solutions to our mathematical problems, to establish hierarchies of scarcity and abundance, and to prove that certain infinities are fundamentally smaller than others. The psychological mechanism driving our fascination with such conjectures involves our deep-seated need to impose order on mathematical chaos, to create barriers and boundaries that separate the possible from the impossible, and to demonstrate that even in abstract realms of pure mathematics, entropy and containment operate in measurable ways. We have normalized this pursuit of boundedness and finiteness as fundamental virtues in mathematics, accepting that the ultimate achievement is often to prove that infinity, when properly examined, collapses into manageable finitude, and the Bombary-Lang conjecture remains unproven precisely, because it represents this yearning for control over mathematical phenomena that continues to elude our most sophisticated techniques and deepest insights. Consider the peculiar intersection of three-dimensional geometry and quantum mechanics, where mathematicians have long suspected a hidden relationship between the hyperbolic volume of a knot complement and the behavior of quantum invariants at specific mathematical points. The volume conjecture, proposed by Rieger Kashev in the 1990s, emerges from observing that certain quantum invariants evaluated at roots of unity appear to grow in a manner intimately connected to classical geometric measurements that seem to belong to entirely different mathematical universes. When you take a knot, the kind of mathematical object formed by threading a strand through space and joining its ends without cutting, and you calculate its hyperbolic volume, a measurement describing how much curved three-dimensional space surrounds that knot, this number appears mysteriously encoded within quantum calculations that operate on fundamentally different principles. The psychological mechanism driving our fascination with this conjecture stems from humanity's deep intuition that the universe operates under unified principles, that seemingly disparate mathematical frameworks must somehow communicate through hidden channels we have yet to discover. We find ourselves confronted with the uncomfortable reality that quantum mathematics and classical geometry, two languages that describe reality in completely different symbolic vocabularies, appear to whisper about the same underlying truths. What persists despite decades of investigation is our collective bewilderment at how nature could possibly arrange itself such that distinct mathematical domains speak to one another with such apparent precision and intentionality. The volume conjecture remains largely unproven, existing in that liminal mathematical space where tantalizing evidence accumulates without delivering definitive proof, and mathematicians continue testing its boundaries against increasingly exotic knots and quantum frameworks, searching for the fundamental bridge that would finally explain why geometry and quantum mechanics should know anything about each other at all. In the field of topology, mathematicians encounter a peculiar problem that sits at the intersection of three-dimensional space and four-dimensional abstraction, known as the slice-ribbon conjecture, which concerns itself with the nature of knots and their fundamental properties when examined through increasingly abstract mathematical lenses. When a knot exists in three-dimensional space, it possesses certain characteristics that mathematicians can measure and analyze, yet when that same knot is embedded into four-dimensional space, something profound occurs. Certain knots that appear impossibly tangled in our familiar three dimensions can suddenly become untangled, suggesting that dimension itself operates as a kind of liberation for geometric entanglement. The slice-ribbon conjecture proposes that every ribbon knot, a knot with particular geometric properties that allow it to exist on a ribbon-like surface without self-intersection, must also be a slice knot, meaning it could theoretically be the boundary of a smooth disk in four-dimensional space. The psychological mechanism underlying this conjecture relates to our human tendency to seek elegant unification and symmetry in mathematics, where we anticipate that if a knot possesses one special property, it should naturally possess all related special properties, creating a hierarchical structure of mathematical objects that feels intuitively correct even without proof. For decades, mathematicians have observed that every known ribbon knot indeed appears to be a slice knot, leading to a cumulative confidence in the conjecture despite the absence of rigorous proof, and yet counterexamples remain stubbornly elusive, existing somewhere in the vast landscape of unknown mathematical territory. The persistence of this unproven statement within mathematical literature represents a fascinating normalization of uncertainty, where the mathematical community continues to build research upon assumptions that remain fundamentally unverified, accepting that intuition and pattern recognition can guide exploration even when logical completion remains forever out of reach. Consider the peculiar mathematical landscape where topology and differential geometry collide, where mathematicians have spent decades attempting to determine whether every smooth, simply connected closed manifold of dimension 4 is equivalent to the four-dimensional sphere, a question that emerged from Henri Poincaré's original conjecture, but has proven itself to be fundamentally different in character and stubbornness from its higher and lower dimensional counterparts. The smooth Poincaré conjecture in dimension 4 represents a specific and vexing reformulation of the broader topological Poincaré conjecture, which itself asked whether a three-dimensional space that is topologically indistinguishable from a three-sphere must actually be a three-sphere, a question that was eventually resolved through the work of Grigori Perelman in the early 2000s using sophisticated techniques from geometric analysis and flow equations. However, the smooth version in four dimensions remains defiantly unresolved, creating a curious intellectual cavity where the topological question has been answered, but the geometric refinement persists in shadow, suggesting that there may be obstructions arising from the particular and peculiar properties of four-dimensional space itself, where smooth structures behave in strange ways that higher and lower dimensions do not exhibit. The psychological mechanism underlying this persistence involves a kind of mathematical incompleteness that challenges our intuitions about dimensional spaces, for we might expect that if a problem is solved in dimension 3 and dimension 5 and higher, then dimension 4 should yield relatively easily. Yet the reality is that four-dimensional smooth structures admit exotic variations and counterintuitive phenomena that make the smooth Poincaré conjecture remain stubbornly beyond the reach of known techniques. Imagine a piece of string twisted and looped in the most intricate ways possible, knotted so complexly that it seems to defy any simple understanding of its true form, and consider that mathematicians have spent decades studying whether certain knots possess a peculiar and elusive property that would fundamentally transform how we understand three-dimensional topology. The Burge knot conjecture, proposed by mathematician Jean Burge in the 1970s, concerns itself with a very specific question about knots whose properties seem to vanish entirely when you perform a particular operation called lens space surgery, creating what appears to be a simple loop where once existed something far more complicated. The conjecture suggests that if a knot can be transformed into a lens space through Dehn surgery, then that knot must belong to a very restricted family of knots called doubly primitive knots, which possess symmetries and structural properties that make them remarkably special and rare within the broader universe of all possible knots. What makes this conjecture so psychologically compelling is that it represents humanity's deep need to classify and categorize infinite complexity into neat, orderly families. Yet the mathematical machinery required to prove such relationships remains frustratingly opaque and resistant to conventional approaches. For decades, the conjecture resisted all attempts at proof, standing as a monument to the possibility that certain truths about three-dimensional space might require entirely new mathematical languages or insights that simply have not yet been invented. The conjecture has gradually yielded to partial proofs in specific cases, yet the complete picture remains elusive, haunting mathematicians with the suspicion that some knots might exist in shadowy corners of topology where our intuitions about space completely break down, reminding us that even after centuries of mathematical refinement, the structure of three dimensions still holds mysteries that resist our most determined attempts at comprehension. Consider the abstract landscape of topological group theory, where mathematicians have spent over a century contemplating a deceptively simple yet profoundly elusive question about the nature of transformation and continuity. The Hilbert-Smith conjecture, proposed in various forms throughout the early 1900s, asks whether every locally compact group that acts on a manifold must itself be a Lie group, and more specifically, whether a p-adic group could ever perform such an action in a manner that preserves the fundamental structure of the space. This question emerged from a genuine mathematical curiosity about what kinds of symmetries and transformations could exist in geometric spaces. Yet it has resisted resolution through every available technique despite being understood by only a small fraction of mathematicians working today. The conjecture touches something deeply counterintuitive about the nature of continuity and discrete mathematics, suggesting boundaries between what can and cannot happen in higher dimensional spaces that we cannot directly visualize or comprehend through ordinary experience. What makes this conjecture particularly disorienting is that partial results have emerged, with mathematicians proving it true in certain restricted contexts, such as for manifolds of dimension 3 or below, yet the general case remains tantalizingly beyond reach, as though the conjecture hovers in some liminal space between true and false. The psychological persistence of this unsolved problem reflects how mathematics operates at the intersection of pure abstraction and mysterious constraint, where we sense that certain truths must exist, yet cannot force them into the light of proof, leaving mathematicians to circle endlessly around its perimeter, finding new angles of approach, but never quite reaching through the veil that separates knowledge from ignorance, certainty from profound mystery. The Zeeman Conjecture, formulated by mathematician Christopher Zeeman in the 1960s, ventures into the topological realm of what mathematicians call collapsibility and contractibility, two concepts that seem intuitively similar yet remain maddeningly difficult to prove equivalent in higher dimensions. The conjecture posits that every contractible compact polyhedron is collapsible, which is to say that if a geometric structure can be continuously shrunk down to a single point without tearing or creating holes, then it should theoretically be able to be built up from a single point by successively gluing on simple geometric blocks, a process called collapsing that works remarkably well in lower dimensions. In 2 dimensions, this relationship holds with elegant certainty, and in 3 dimensions, the statement remains unproven despite decades of focused mathematical effort, yet no counterexample has ever been discovered to definitively disprove it. Mathematicians have constructed increasingly sophisticated topological objects, abstract spaces that exist only in mathematical imagination, and each time they find that Zeeman's intuition somehow holds true, even as proof remains perpetually out of reach. The psychological mechanism at work here involves our deep human expectation that mathematical truths should exhibit consistency and symmetry across dimensional scales, and our profound discomfort with the possibility that something simultaneously true and false could exist in mathematical reality. We have normalized the uncertainty surrounding this conjecture by acknowledging that some questions may require entirely new mathematical frameworks to solve, yet we remain unsettled by a proposition so reasonable that it refuses to yield to traditional proof techniques, creating an enduring gap between our mathematical intuition and our ability to validate it rigorously. Consider a mathematical space where we attempt to measure the size of sets using what mathematicians call Hausdorff dimension, a concept that extends our intuitive understanding of dimension beyond the familiar 3 or 4 we experience in ordinary life. The Borel conjecture, posed by the French mathematician Émile Borel in the early 20th century, presents a deceptively simple question that has resisted resolution for over a century. It asserts that every analytic set in Euclidean space that has sigma-finite Hausdorff measure in its dimension must necessarily be countable. The real-life situation here involves the fundamental tension between what we can construct mathematically and what the universe of sets actually permits to exist. When mathematicians work with these exotic spaces and their dimensional properties, they encounter the peculiar phenomenon where certain sets seem to occupy intermediate positions, neither clearly finite nor clearly infinite in their fundamental nature. The psychological mechanism underlying this conjecture reflects a deep human expectation that mathematical reality should behave predictably and that measures should translate cleanly into cardinality. Yet the conjecture remains unproven precisely because the mathematical universe appears to harbor ambiguities that resist our categorical thinking. The conceptual difficulty lies in reconciling two different ways of understanding size: the measure-theoretic approach, which assigns quantities of length or area or volume, and the cardinality approach, which counts elements directly. We have essentially normalized this unresolved tension by treating it as a routine open problem, one among thousands, when in fact it represents a fundamental gap in our understanding of how dimensional properties relate to set-theoretic size. Deep within the architecture of algebraic topology and geometric group theory lies a proposition so fundamental that its resolution would reshape our understanding of how mathematical structures behave across multiple dimensions and algebraic systems. The Farrell-Jones conjecture, formulated in the 1990s by Tom Farrell and Lowell Jones, makes a deceptively simple claim about the relationship between K-theory and L-theory of group rings and their connections to assembly maps that translate local information into global invariants. Essentially, the conjecture proposes that certain computations in these abstract algebraic spaces can be reduced to studying them over finite subgroups, a property that would allow mathematicians to understand vastly complex structures by examining their simpler building blocks. What makes this conjecture so perplexing is that despite decades of intense research and partial verifications across numerous specific cases, we still cannot determine whether this elegant reduction principle holds universally across all possible groups and all mathematical contexts in which it might apply. The psychological mechanism at work here involves our deep intuition that complexity should decompose into simpler components, that the whole should be understandable through careful examination of its parts. Yet the conjecture resists proof precisely because certain pathological groups and exotic mathematical structures seem to violate our expectations about how assembly should work. Mathematicians have verified the Farrell-Jones conjecture for large families of groups including hyperbolic groups, soluble groups, and arithmetic groups, each verification lending credence to its universality, yet each specific case that succeeds paradoxically deepens the mystery of why a universal proof remains so elusive. Imagine a three-dimensional space where smooth surfaces exist in a state of perpetual motion, flowing and twisting through geometric dimensions in ways that defy our ordinary intuition, and the Weinstein Conjecture asks a deceptively simple question about whether certain paths must necessarily exist on these surfaces, regardless of how they curve or transform through space. Named after the mathematician Alan Weinstein, this conjecture emerges from the field of symplectic geometry, a branch of mathematics that studies spaces with a particular kind of geometric structure, and it posits that every contact manifold must contain at least one closed orbit, a path that returns to its starting point and traces out a loop in the ambient space. The psychological difficulty here lies in the fact that while this seems intuitively obvious when we consider physical systems in nature, where energy conservation and smooth dynamics typically force periodic behavior to emerge, proving this simple-sounding statement has proven extraordinarily resistant to mathematical proof, challenging our assumption that fundamental truths should be easy to verify once we understand them clearly. Mathematicians have spent decades attacking this problem from multiple angles, translating it into different languages of geometry and topology, yet the core resistance persists, suggesting that reality has hidden layers of complexity beneath what appears to be a straightforward geometric assertion. We have normalized this gap between intuition and proof in mathematics, accepting that some conjecture statements can feel almost self-evident while remaining mathematically elusive, and the Weinstein conjecture sits in this uncomfortable space where our geometric intuition insists something must be true while our analytical tools struggle to articulate precisely why. Leaving us to contemplate whether our fundamental understanding of smooth spaces and periodic motion contains gaps we have yet to perceive, or whether the proof simply awaits discovery in mathematics, yet unexplored. Imagine a bath filled with water, and as you watch, thousands of tiny bubbles form and cling together on the surface, creating a delicate foam that seems to defy the most basic principles of stability and order. This is the phenomenon that has captivated Lord Kelvin and mathematicians for nearly 2 centuries, a problem so deceptively simple in appearance, yet so profoundly complex in its implications, that it remains one of the most elegant unsolved puzzles in geometry and physics. The question asks something that sounds almost trivial. What is the most efficient way to divide three-dimensional space into equal volume cells with the minimum surface area? A problem directly observable when foam naturally organizes itself into patterns that should theoretically follow mathematical rules, but somehow resist our attempts to prove which arrangement is truly optimal. When you look at a bubble in foam, you see curved walls meeting at precise angles, and the bubbles seem to know, through some invisible geometric intelligence, exactly how to arrange themselves to conserve energy and minimize surface tension. Yet we cannot definitively say that what we observe is the absolute best solution nature could possibly achieve. The Kelvin structure, proposed in 1887, was believed for over a century to be the answer, a tetracadecahedron arrangement so elegant and seemingly perfect that it satisfied the mathematical intuition of nearly every researcher who encountered it. Until in 1993, a counterexample was discovered, proving that even this beautiful solution was not the ultimate truth. What makes this problem so psychologically unsettling is that foam itself seems to solve it effortlessly, that simple physics and surface tension appear to find the answer through blind physical processes. Yet human mathematics cannot verify or prove what the foam already knows, creating a strange gap between observable nature and mathematical certainty that refuses to close.